In this presentation we will introduce the fundamental equation of dynamics and apply it in different types of motion. The content of this presentation is the following. We will start with the introduction of the fundamental equation of dynamics based on the laws of motion. Then we will apply the fundamental equation in several examples where we study dynamics in a variety of problems. First, we analyze the dynamics of projectile motion and Hooke's law related to simple harmonic motion. Then we study constrained motion and constrained forces with the examples of moving bodies over horizontal and inclined planes, and present Atwood machine using constrained forces. Frictional motion is the next topic where we consider the same examples, that is moving bodies over horizontal and inclined planes, and present Coulomb's law of friction. We also study forces exerted on objects moving along curves, such as circles or curves with some general shape. Then we discuss the dynamics of a mathematical pendulum performing a periodic motion for small swings and in the general case as well. We will continue the dynamics of a periodic motion with planetary motion and present Kepler's three laws describing celestial motion in the solar system. This topic leads us to the introduction of Newton's law of gravitation describing the universal effect of gravitational mass, where we present Cavendish experiment demonstrating the law. We finish this presentation with D'Alembert's principle, which provides the static interpretation of force and the fundamental equation of dynamics. As a preparation for our study on the fundamental equation of dynamics, we will give a brief summary of the basic assumptions and the laws of dynamics. In our analysis on motion in dynamics, we concluded that material bodies have effects on the motion of other bodies. Although these external effects cannot be eliminated completely, we can reduce them, which indicates that bodies free from such effects stay at rest or hold their uniform rectilinear motion with respect to a special frame of reference, called inertial frame of reference. As a result of this assumption known as the first law of motion, the acceleration of a given body is due to the effect of other bodies, and we consider this effect as a force acting on the body. Here the ball rolling along a straight line collides a greater ball at rest and changes its course. The effect of the greater ball on the motion of the rolling ball can be represented by the force F. Based on measurements providing a quantitative description on these effects on the state of motion of bodies, we assume that the greater the force acting on the body is, the greater the acceleration and the mass of the body are. The mass of the body is a quantity which only depends on the physical properties of the given body. We establish the quantitative relation between the force F acting on the body and the acceleration a and the mass m of the body by applying the simplest possible definition, stating that the force F is equal to the product of the mass m and the acceleration a. This definition, known as the second law of motion, allows us to measure the mass and the force by applying dynamic methods, if we suppose that the same measurement apparatus exerts the same force on different bodies. The third law of motion states that the action and reaction between two bodies are equal in magnitude and opposite in direction. In other words, the force FAB exerted on the body A by the body B is equal to minus the force FBA exerted on the body B by the body A. We can recognize the importance of this law when we study the motion of systems of several bodies. The fourth law of motion assumes that forces acting in the interactions between bodies can be described by vectors. If the bodies B and C collide with the body A at the same time, then their effects on the state of motion of the body A can be represented by the forces FAB and FAC. These forces are vectors, since the result of the collision experiment shows that the net effect of the two bodies B and C can be represented by the net force equal to the vector sum of the forces FAB and FAC. The static measurement of force and mass is based on this law, where we use the fact that 2 point-like bodies stay at rest if the two forces acting on them are equal in magnitude and opposite in direction. The static measurement of mass also uses the fact that the gravitational acceleration is the same everywhere on Earth. As a result, we could establish another fundamental law of nature called equivalence principle, stating that the gravitational mass of a body measured by a weighing scale is equal to its inertial mass, which appears in the second law of motion. We can combine the second law of motion with the fourth law, where the result is called the fundamental equation of dynamics. The fundamental equation states that the product of the mass m of a point-like body and its acceleration a with respect to an inertial frame of reference is equal to the net force F acting on the body. If r is the position vector of the body with respect to a given reference point O, then this equation states that the mass m times the second-order derivative of the position vector r of the body with respect to the time t is equal to the net force F, where F is equal to the vector sum of all the forces F1, F2, ellipsis, Fn acting on the body. We can apply the fundamental equation of dynamics in two different ways in the study of motion of point-like bodies. If we observe the trajectory of a body, described by its position vector r as a function of the time t, then we can determine its acceleration a, which is the second-order derivative of the position vector r with respect to the time t. If we know the acceleration of the body, then we can determine the force F acting on the body from the equation stating that the force F is equal to the mass m of the body times its acceleration a. This kind of application of the fundamental equation is very important if we are able to find a whole class of motions, where the mathematical expression of the force related to each type of motion in the class is the same. Such a mathematical expression describing the force related to the motions of a given class is called law of force. The second way to apply the fundamental equation is to follow the opposite direction. For a given law of force, we determine the forces acting on a body, and compute the net force F by applying the parallelogram law. Then the fundamental equation will tell us that the acceleration of the body given by the second-order derivative of its position vector r is equal to the net force F divided by the mass m of the body. By integrating this equation, we can determine the position vector r of the body as a function of time, that is, we can describe the trajectory of the body during its motion. Let us consider some examples for the first way to apply the fundamental equation of dynamics. In the first example, we present the law of force for the motions of freely falling objects and projectiles. Galileo in his experiments demonstrated that the motions of bodies in free fall and projectiles belong to the same class related to the gravitational acceleration, where the law of force is the gravitational force or the weight of the bodies. This law of force can be derived from the observation of free fall or projectile motion, if the force of air resistance acting on the moving body is neglected. Galileo found that the distance s which a falling body covers in a given time is always proportional to the square of the time t measured from the beginning of the free fall. Since the body moves along a straight line, we can conclude that the speed v of the falling object is proportional to the elapsed time. Therefore its change of rate or acceleration a is constant and points downwards, in the direction of the motion. We denoted the acceleration of a body in free fall by the letter g, and called it gravitational acceleration. Then the law of force for gravity is given by the equation stating that the force F acting on a body in free fall is equal to the mass m of the body times the gravitational acceleration g. This is the law of force for projectiles with negligible air resistance as well, since the horizontal component of its motion can be described as a uniform rectilinear motion, whereas its vertical component is a free fall with the acceleration g. The second example considered here is the class of simple harmonic motions. In the study of simple harmonic motion, we presented some experiments with oscillating bodies suspended from springs. The results showed that the acceleration a of a body performing such a motion is equal to minus the ratio of 4 pi squared to the square of the period t of the motion, times the displacement x of the body from its equilibrium position. If the mass of the body is m, then the law of force for the simple harmonic motion of the body states that the force F acting on the body is equal to minus m times the ratio of 4 pi squared to t squared, times x. However, the experiments applying springs also demonstrated that if the mass of the spring is negligible with respect to the mass m of the oscillating body, then a body of the mass 2 times m or 3 times m performs simple harmonic motion where the square of the periods t is also 2 times or 3 times greater than t squared measured in the original case. Therefore the factor 4 pi squared times m divided by t squared in the force law is independent from the mass m, that is, the factor is constant, which is completely determined by the geometry and the physical properties of the spring. As a result, we obtain a law of force stating that the force F acting on the body in the direction of its motion is equal to minus the spring constant k times the amplitude x of the oscillation. It is called the modified version of Hooke's law, describing the restoring force exerted by the spring on its fixed end. In the original version of Hooke's law, the force applied on the string to stretch or compress it in the negative sign is missing from the right-hand side of the law of force. The modified version of Hooke's law states that the direction of the restoring force is opposite to that of the displacement and its magnitude is directly proportional to the displacement. The general form of the law of force for quasi-elastic forces states that the magnitude of a force F directed towards a center O is proportional to the distance r of the center from the point P where the force is applied. In other words, the force F exerted by a body against deformation forces is equal to minus a constant k, times the displacement vector r pointing from the center O to the point P. The spring constant k can be determined by applying the static measurement of force. We can suspend a series of weights with different masses from the spring and measure the stretch of the spring for each weight in balance. By calculating the ratios of each weight to the length of the stretch, we obtain a series of data points on the weight versus displacement plot. If we fit a line on the measured data points in the linear regime, then its tangent will give the spring constant k. A third example for the application of the fundamental law of dynamics is related to the general motions governed by Newton's law of gravitation. Newton derived this law from empirical observations of planetary motion establishing the orbital motion of the Earth and the Moon. He applied his second and third laws of motion to explain the orbital motion of these planets, and he could deduce the universal law of gravitation. This law of force states that the magnitude of the attractive force F acting between 2 point masses m1 and m2 separated by the distance r is equal to a universal constant g, multiplied by the product of the masses m1 and m2, and divided by the square of the distance r. The force acts in the direction of the vector r joining the two bodies. The law of action and reaction also states that the bodies exert equal but opposite gravitational forces on each other. Since Newton's law of gravitation is a universal law, it can be studied in lab experiments as well, where the gravitational constant g was measured to a high precision. We have mentioned only 3 different laws of force here, but there are many other types of law of force, for example those which are related to friction or air resistance, and we can also talk about buoyant forces or the force acting between charged bodies, and so on. We have seen that the second way to apply the fundamental equation of dynamics follows the opposite direction, where we determine the motion of a body from a given law of force describing forces acting on it. For the sake of brevity, let us start with the rectilinear motion of a point-like body with respect to some frame of reference. We can attach a Cartesian coordinate system to the frame of reference such that the body travels along its x-axis, and its instantaneous position is described by its x-coordinate as a function of time. Then the fundamental equation of dynamics has only one component along the x-axis, which is the equation of motion of the body. The equation of motion states that the mass m of the body times the second-order derivative of its x-coordinate with respect to the time t is equal to the x-component of the force F acting on the body. Since the body moves along the x-axis, the y and z components of the force F must vanish. As a result, the motion of the body is completely determined by the x-component of the force. In the general case, the component fx can depend on the position x of the body, the first-order derivative of the coordinate x with respect to the time t that is the speed of the body, and the time t itself. The equation of motion is a second-order differential equation, and we can determine the motion of a point-like body by solving an initial value problem for this equation. In other words, for a given initial value condition, that is for a given position x0 and a given velocity v0x of the body at the time t equal to 0, we solve the differential equation. By solving the equation with this initial data, we obtain the x-coordinate as a function of time describing the instantaneous position of the body along the x-axis during its motion. In the case of spatial motion, the instantaneous position of a moving point-like body is described by the position vector pointing from a reference point O representing the frame of reference to the position of the body. Then the fundamental equation of dynamics is a vector equation, stating that the mass m of the body times the second-order derivative of its position vector r with respect to the time t is equal to the force F acting on the body. In the general case, the force F depends on the position of the body, its velocity given by the first-order derivative of the position vector, and the time t. The position of a point-like body can also be described in a Cartesian coordinate system attached to a frame of reference by the coordinates x, y and z as functions of the time t. Then the equations of motion for the body can be expressed in Cartesian coordinates, stating that the mass m times the second-order derivative of the x-coordinate of the body with respect to the time is equal to the x-component of the force F acting on the body. The two other equations of motions have the same form with the components y and z of the vector equation. The components x, y and z of the force F acting on the body are functions of the coordinates, their first-order derivatives with respect to the time t, and the time t itself. The equations of motion form a system of second-order differential equations. If we want to determine the trajectory of the moving body that is its Cartesian coordinates as functions of time, we need to solve an initial value problem for this system. As an initial value condition, we have to prescribe the initial coordinates x0, y0 and z0, and the initial velocity components v0x, v0y and v0z of the body at the time t equal to 0. The initial position and velocity of the body are arbitrary initial data, which determine the unique solution for the coordinate functions x, y and z obtained by solving the system of differential equations. The fact that given forces acting on a body and the initial data of its position and velocity uniquely determine the motion of the body, is equivalent with the principle of causality in mechanics. Such a quantitative study was only allowed by the introduction of the concept of the force in the second law of motion stating that the force F acting on the body is equal to its mass m times its acceleration a. When we say that the acceleration of an object is produced by a net force acting on it, that is, a force causes it to accelerate, it is just a simplified expression of the fact that we have to find the real causes of its acceleration in the geometric and physical state of other bodies at various distances of the object. We have already mentioned projectile motion as an application of the fundamental equation of dynamics in the deduction of laws of force. Now we use the law of force for gravity to derive the equations of motion for projectiles. If we study the motion of a point-like body with the mass m under the influence of the gravitational force F with respect to the ground as a frame of reference, we can consider the projectile launched from an arbitrary point P with the initial velocity v0, where the angle between the direction of the velocity and the horizontal direction is denoted by alpha. We can choose a reference point O on the surface of the ground to describe the instantaneous and initial positions of the body by the position vectors r and r0, respectively. The fundamental equation of dynamics for such a motion states that the mass m of the body times the second-order derivative of the position vector r with respect to the time t is equal to the gravitational force F, which is given by the mass m times the gravitational acceleration g. As a result, the equation of motion of the point mass m states that the second-order derivative of the position vector r with respect to the time t is equal to the gravitational acceleration g. Since the mass m is eliminated from this equation, we can conclude that the motion of the body is independent of its mass. In the discussion on freefall, we saw that the gravitational acceleration g can be assumed as a constant, if the motion is limited to a small region near Earth's surface. This approximation allows us to attach a Cartesian coordinate system to the reference point O such that the z-axis is oriented in the opposite direction to gravity. Then the position vector r is given by the coordinate functions x, y and z, and the initial position of the projectile has the coordinates x0, y0 and z0. Similarly, the Cartesian components of the initial velocity of the moving body are denoted by vx, vy and vz, and those of the gravitational acceleration g are 0, 0, minus the magnitude of g. As a result, the equations of motion of the point mass state that the second-order derivative of the x and y coordinates of its instantaneous position respect to the time t vanish, whereas the second-order derivative of the z-coordinate with respect to the time t is equal to minus the magnitude g. By integrating these differential equations, we obtain that the x-component of the velocity v of the moving body, that is the derivative of the x-coordinate with respect to the time t, is equal to a constant c1. Similarly, the y-component of the velocity v, that is the derivative of the y-coordinate with respect to the time t, is equal to a constant c2. The z-component of the velocity v, that is the derivative of the z-coordinate with respect to the time t, is equal to minus the gravitational acceleration g times the time t, plus a constant c3. Here the constants c1, c2 and c3 are arbitrary integration constants. If we integrate the Cartesian components of the velocity v, we obtain the coordinate functions describing the instantaneous position of the moving body. Then we can write that the x-coordinate of the projectile is equal to c1 times the time t, plus a constant b1. Its y-coordinate is given by c2 times t plus a constant b2. Finally, its c-coordinate is equal to minus 1 over 2 times g times t squared, plus c2 times t, plus a constant b3. Here the constants b1, b2 and b3 are also arbitrary integration constants. The coordinate functions x, y and z with the 6 arbitrary constants are the general solutions of the equations of motion. Therefore the general solutions provide all the possible motions of a body under the influence of gravity. When we solve the initial value problem for projectile motion, we substitute the initial data into the general solution to obtain a particular solution of the equations of motion. The initial value condition for the equations of motion specifies the initial position r0 at the point P and the initial velocity v0 of the point mass at the initial time of 0 second. Then the initial data are given by 6 constants. The initial coordinates x0, y0, and z0 for the initial position of the body, and the components v0x, v0y and v0z of its initial velocity. We saw that the general solution of the equation of motion states that the x-component of the instantaneous velocity of the projectile is equal to the integration constant c1, and its y-component is given by the integration constant c2. The z-component of the initial velocity is equal to minus g times t, plus c3. Similarly, the general solution of the equation of motion consists of the following coordinates describing the instantaneous position of the projectile. The x-coordinate of the point-like body is equal to c1 times t plus b1, its y-coordinate is given by c2 times t plus b2, and its z-coordinate is equal to -1 over 2 times g times t squared, plus c3 times t, plus b3. If we substitute the initial values specified in the condition into the general solution for the time t equal to 0 second, we can express the integration constants in the terms of the initial data. Then we see that the constants c1, c2 and c3 are equal to v0x, v0y and v0z, respectively. That is, these integration constants are the components of the initial velocity v0 of the point-like body. Similarly, the constants b1, b2 and b3 are equal to x0, y0 and z0, respectively. That is, these integration constants are the coordinates of the initial position of the point mass. Then the instantaneous position of the projectile is given by the following Cartesian coordinates as functions of time. Its x-coordinate is equal to the x-component of its initial velocity v0 times the time t, plus the x-coordinate of its initial position. Similarly, its y-coordinate is given by the y-component of its initial velocity v0 times the time t, plus the y-coordinate of its initial position. Its z-coordinate is equal to -1 over 2 times the magnitude of the gravitational acceleration g times the square of the time t, plus the z-component of its initial velocity v0 times the time t, plus the z-coordinate of its initial position. The instantaneous velocity of the projectile is given by the following Cartesian coordinates as functions of time. Its x and y components are equal to the x and y components of its initial velocity v0, whereas its z-component is given by minus the magnitude of the gravitational acceleration g times the time t, plus the z-component of its initial velocity v0. Finally, the Cartesian components of the acceleration of the projectile is simply 0, 0 and minus the magnitude of the gravitational acceleration g, respectively. Here the kinematic variables of the projectile are described by applying Cartesian coordinates. However, we can also give these vector functions in a coordinate-independent form, stating that the position vector r of the projectile is equal to minus the gravitational acceleration g times the square of the time t, plus its initial velocity v0 times the time t, plus its initial position r0. The velocity v of the projectile is minus the gravitational acceleration g times the time t, plus its initial velocity v0, whereas the acceleration a of the projectile is simply equal to minus the gravitational acceleration g. These are the general expressions for the kinematic variables of a projectile, where the initial position and velocity of the moving body are arbitrary vectors. In fact, they could be expressed in a different coordinate system as well, but the Cartesian coordinates adapted to the trajectory of the motion provide the most convenient description of the motion of the projectile. The best way to adapt such a coordinate system is the following. If we choose the point P of the launch as the reference point O, that is the origin of the Cartesian coordinate system, then the Cartesian components of the initial position vector are 0 vanish. Furthermore, if we orient the x and y axes of the coordinate system such that the trajectory of the projectile remains in the plane spanned by the x and z axes, then the y component of the initial velocity v0 vanishes, and its x and z components can be expressed in the terms of the angle alpha of the launch. That is, Vx is equal to the magnitude of V0 times cosine alpha, and Vz is given by the magnitude of V0 times sine alpha. As a result, the x-coordinate of the instantaneous position or the vertical position of the projectile in such a coordinate system is given by the magnitude of the initial velocity V0 times the cosine of the angle alpha of the launch times the time t. The z-coordinate of the instantaneous position or the height of the projectile is equal to the magnitude of the initial velocity v0 times the cosine of the angle alpha times the time t, minus 1 over 2 times the gravitational acceleration g times the square of the time t. In these equations the initial data are represented by the magnitude of the initial velocity and the angle of the launch, and these two parameters uniquely determine the motion of the projectile. If we express the time t from the first equation and substitute the result into the second one, we immediately see that the z-coordinate of the projectile is a quadratic function of its x-coordinate, that is the trajectory of the projectile is a parabola, as shown in the presentation of the projectile motion in kinematics. The solution of the equations of motion shows that the most general motion of a point mass under the influence of gravity is projectile motion, provided the force of the air resistance acting on the moving body is negligible. We can generalize this result as follows. If the acceleration a of a point mass m is produced by an arbitrary constant force F instead of the gravitational force, then the fundamental equation of dynamics states that the second-order derivative of the position vector r of the body with respect to a reference point O, or its acceleration a, is given by the force F acting on the body divided by the mass m of the body. Since both the force F and the mass m are constant, the acceleration of the body is also constant. As a result, we can treat the fundamental equation in the same way as in the case of the motion of a body with uniform acceleration, where the equations of motion are the following. The instantaneous position vector r of the moving point mass is equal to 1 over 2 times the acceleration a times the square of the time t, plus the initial velocity v0 times the time t, plus the initial position vector r0. The instantaneous velocity v of the moving point mass is given by the acceleration a times the time t, plus the initial velocity v0, where the acceleration a is constant. These equations also demonstrate that if the force F vanishes, that is the acceleration is 0, then we have the special case of the uniform rectilinear motion, where the equations of motion reduce to the equation stating that the position vector r of the body is equal to its initial velocity v0 times the time t, plus its initial position r0, and the velocity v of the body is simply the initial velocity v0 for the vanishing acceleration a. One of the law of force mentioned before is Hooke's law, a special case of quasi-elastic forces. The law of elasticity was discovered by the English physicist Robert Hooke in 1660. In his experiments with the elastic deformation of different materials, he exerted a force on a material and studied how it stretched or compressed in response to the force. He could apply a deformation force to a solid by stretching, compressing, squeezing, bending, or twisting. Hooke examined elastic deformation, which is reversible and non-permanent. This means that the material returns to its original shape and size upon removal of the load. Hooke noticed that the displacement or the size of the deformation of the material is directly proportional to the applied force for relatively small deformations. In other words, the force or stress versus strain curve for many materials has a linear region within certain limits. In the stress versus strain plot, the green area represents this linear region called elastic zone, where Hooke's law is valid. In the plastic zone represented by the blue area, the deformation of the material becomes non-reversible and permanent. The stress versus strain curve is not linear in the stress hardening zone represented by the yellow area, where it reaches its maximum called strain ultimate tensile strength. The curve decreases in the failure zone represented by the red area and ends at the fracture point of the given material. In order to study Hooke's law, we apply a force or strain small enough so that the deformation of any object remains in the elastic zone. We already gave the mathematical form of Hooke's law stating that the applied or the restoring force F is equal to plus or minus a constant k times the displacement x, that is the change in the length of the deformed body. The plus sign is for the applied force and the minus sign is for the restoring force causing the body to return to its original dimensions. As the law of action and reaction states, the applied and restoring forces are equal and opposite in direction. The value of the constant k, called spring constant, has the unit of Newton per meter, and it depends on the material properties, the dimensions, and the shape of the body. Since we study Hooke's law in the context of the derivation of equations of motion from a law of force, we will apply the example of a body suspended from a spring. Then the law force states that the restoring force F causing the string to return to its original shape is equal to minus the spring constant k times its displacement x. If we substitute this law of force into the fundamental equation of dynamics, we can obtain the equation of motion of the body and solve it for the displacement x of the body as a function of time. In kinematics, we already presented an experiment setup where an iron cylinder with the mass m is suspended to compensate its gravitational acceleration, and two springs are also attached to the cylinder. Both the springs are fixed at their other end, as seen in the figure. If we orient the x-axis along the axes of the springs where the cylinder is at rest at the origin, then the body can move a short distance along the x-axis in both directions, expanding and compressing the springs. As a result, the springs exert a net restoring force F on the moving body, where the magnitude of the force is proportional to the displacement x of the cylinder and points in the opposite direction of its motion. In this coordinate system, the only non-vanishing component of the force F is in the x direction, and the fundamental equation of dynamics describing the effect of the net force on the cylinder is the following. The mass m of the cylinder times the second-order derivative of its displacement x with respect to the time t is equal to the x component of the force F. Here the law of force is given by Hooke's law, that is the x component of the restoring force F acting on the cylinder is equal to minus the spring constant k times the displacement x of the body. The spring constant k represents the total effect of both the springs attached to the cylinder. Then the equation of motion states that the mass m of the body times the second-order derivative of the displacement x with respect to the time t is equal to minus k times the displacement x. If we introduce the variable omega squared defined as the ratio of the spring constant k to the mass m, we can write the equation of motion in the form stating that the second-order derivative of the displacement x with respect to the time t is equal to minus omega squared times the displacement x. The general solution of this differential equation provides the displacement x function of time, which is equal to a constant c1 times the sine of omega times t, plus a constant c2 times the cosine of omega times t. Here c1 and c2 are the integration constants of the solution to the second-order differential equation. The derivative of this equation gives the x component of the velocity v of the body, which is equal to c1 times omega times the cosine of omega times t, minus c2 times omega times the sine of omega times t. The derivative of this equation gives the x component of the acceleration a of the body, which is equal to minus c1 times omega squared times the sine of omega times t, minus c2 times omega squared times the cosine of omega times t. Then the x component of the acceleration a of the body is equal to minus omega squared times its displacement x, as seen in the presentation of simple harmonic motion in kinematics. The y and z components of all these kinematic quantities obviously vanish in the one-dimensional motion along the axes of the springs. For the initial value condition at the time t equal to 0 second, we can specify the initial displacement x0 and the x component of the initial velocity v0 of the body. By substituting these values into the general solutions for t equal to 0 second, we can express the integration constants in terms of the initial data. Then we can see that c1 is equal to the ratio of the x component of the initial velocity v0 to omega, and c2 is equal to the initial displacement x0. As a result, the displacement x of the body can be written as the ratio of the x component of its initial velocity v0 to omega, times the sine of omega times the time t, plus the initial displacement x0 times the cosine of omega times the time t. Here the initial data x0 and v0x are arbitrary constant and they uniquely determine the motion of the body for a given omega, that is for a given mass m and a given spring constant k. This equation can be simplified by introducing the new variables a and alpha such that the following two equations hold. The first equation states that the ratio of the x component of the initial velocity v0 to omega is equal to a times cosine alpha, whereas the second one states that the initial displacement x0 is equal to a times sine alpha. These new variables can also be written in terms of the initial data. If we add the squares of these equations together, we can express the variable a as the square root of the sum of x0 squared and the square of v0x divided by omega. If we divide the second equation by the first one, we can express tangent alpha as the ratio of omega times x0 to v0x. By substituting the new variables into the unique solution to the equation of motion, we can write the displacement x as a times cosine alpha times the sine of omega times t, plus a times sine alpha times the cosine of omega times t. The right-hand side of the equation is simply equal to a times the sine of the quantity of omega times t plus alpha. This solution demonstrates that a point mass m performs a simple harmonic motion under the influence of the quasi-elastic force Fx equal to minus k times x, where the displacement x of the point mass is equal to the maximum amplitude a times the sine of the quantity of the angular frequency omega times the time t plus the phase angle alpha. The angular frequency of the oscillation is given by the square root of the ratio of the spring constant k to the mass m, whereas the maximum amplitude a and the phase alpha of the oscillation are determined by the initial conditions for the displacement and the velocity of the body. The period t of the oscillation given by 2 pi over the angular frequency is equal to 2 pi times the square root of the ratio of m to k. We can choose the turning point of the oscillation as the initial displacement x0 of the body, where the x component of its velocity v vanishes, that is the x component of its initial velocity v0 is equal to 0. This is the case where we pull the cylinder right to a given position x0, and let it oscillate between the positions x0 and minus x0. Then the maximum amplitude a is equal to the initial displacement x0 of the body, which can be seen by substituting the vanishing x component of the initial velocity into the expression for a. Similarly, at the turning point the phase angle alpha in the argument of the sine function is equal to pi over 2, or 90 degrees, which can also be seen if we substitute the vanishing initial velocity into the expression for tangent alpha. As a result, The displacement x of the body for the initial position at the turning point is given by the initial displacement x0 times the sine of the quantity of omega times t plus pi over 2, which is equal to x0 times the cosine of omega times t, as the graph shows. In this special case, the parameters of the motion are the maximum amplitude a of the oscillation, which is given by the initial displacement x0 of the body, and the angular frequency omega of the motion, which is determined by the ratio of the spring constant k to the mass m of the body. Since the cylinder in this experiment is suspended such that the gravitational force acting on the body is compensated, gravity has no role in its simple harmonic motion. However, if we suspend a body from a spring itself, we have to take into account the gravitational force in the fundamental equation of dynamics. Let us consider a body with a mass m suspended from a spring with the spring constant k, where we hold the body in our hand to compensate the weight of the body and prevent the spring from stretching. Here the position of the body is denoted by the origin O, which is located on the x-axis pointing downwards. If we release the body, then it will stretch the spring and it starts to oscillate around the origin O bar, where the distance between the points O and O bar is given by the mass m times the magnitude of the gravitational acceleration g divided by the spring constant k. We can describe this behavior by supplementing the force term in the fundamental equation of dynamics with the gravitational force acting on the body. That is, the x component of the force F in the equation is equal to the spring constant k times the displacement x of the body given by Hooke's law, plus the mass m of the body times the magnitude of the gravitational acceleration g due to the gravitational force. As a result, the equation of motion for the body suspended from the spring is the following. Its mass m times the second order derivative of its displacement x with respect to the time t is equal to minus k times x, plus m times g, which is equal to minus k times the quantity of x minus m times g divided by k. If we introduce the variable x bar defined by x minus m times g divided by k, then the equation of motion states that the second order derivative of the variable x bar is equal to minus omega squared times x bar. Here omega squared is still defined by the ratio of k to m. This is the same equation as the equation of motion describing the horizontal harmonic motion of the cylinder, and the only difference is that the displacement x bar measured from the origin O bar. Then the solution to this equation states that x bar is equal to the maximum amplitude a times the sine of omega times the time t plus a phase angle alpha. Therefore we can conclude that a body with a mass m suspended on the spring with the spring constant k performs a simple harmonic motion around its equilibrium position shifted by the distance of m times the magnitude of the gravitational acceleration g divided by k. If the mass of the spring is not negligible but small compared to the mass of the body, then each part of the spring performing a harmonic motion with different acceleration has to be taken into account in the fundamental equation of dynamics. The greater the distance of a given part of the spring from the body is, the smaller the amplitude of its oscillation is, and this effect modifies the motion of the body as well. For such a problem, it is easier to derive the equation of motion from the law of the conservation of energy instead of applying the fundamental equation of dynamics. Here we only show the resulting equation since the details of its derivation can be discussed after the introduction of the concept of energy and the presentation of the law of its conservation. Then the equation of motion states that the quantity of the mass m of the body plus the mass ms of the spring divided by 3, times the second order derivative of the displacement x bar is equal to minus the spring constant k times the displacement x bar. Here the factor m plus ms divided by 3 is called the reduced mass mr of the body, which can be written as m times the quantity of 1 plus the ratio of ms to 3 times m. We have the same equation of motion as in the case of the spring with the negligible mass, only with the reduced mass mr instead of the mass m of the body. Then the forms of the equations describing the kinematic quantities of the oscillation of the body remain the same, only the reduced mass has to be replaced with the mass m. For example, omega squared is equal to the spring constant k divided by the reduced mass mr, telling us that the angular frequency of the oscillation of the body is smaller than the angular frequency measured in the case with the spring of a negligible mass. As a result, the period t of the oscillation given by 2 pi times the square root of mr divided by k is greater than the period for the case of the spring with a negligible mass. Such a correction can be interpreted as the force F acting on the oscillating body with the mass m is smaller than k times x bar by the factor of 1 plus ms divided by 3 times m. As opposed to simple harmonic motion produced by a spring or planetary motion which are unconstrained motions, in the case of constrained motions, objects move along fixed curves or surfaces. For example, while a body moves along a curved track or slides on a table or a slope, it has to stay in contact with the surface of the track, the table or the slope. In such a situation, the body is forced to move in a restricted way, that is, restrictions are imposed on the motion or position or both of a body, which are known as the constraints limiting its motion. Mathematically, constraints are given by the equations describing the geometric elements restricting the motion of the point-like bodies. These geometric elements are normally curves and surfaces, and the equations describing them can be constructed by applying a coordinate system adapted to the trajectory of the constrained motion. In the case of a ball rolling on the floor, the constraint imposed on the motion of the ball tells us that the ball can only move in the horizontal plane determined by the floor. If the ball is rolling down a ramp, then the constraint restricts its motion along the surface of the ramp. For the horizontal motion, we can attach a Cartesian coordinate system to the floor considered as a frame of reference such that its x-axis oriented along the surface of the floor, and its y-axis is perpendicular to this surface. For the motion on the ramp, we can orient the x-axis of the Cartesian coordinate system along the surface of the ramp, while its y-axis is perpendicular to the surface. Then the constraint for the moving ball is described by the equation stating that the coordinate y of the position of the center of the ball is constant during its motion in both cases. If we consider the ball as a point mass, then we can state that the y-coordinate of the position of the moving ball remains 0. For the circular motion of a point mass m, the frame of reference is attached to the center O of the trajectory of a point-like body, which can be chosen as the center of a polar coordinate system with an x-axis pointing in an arbitrary direction in the plane of the motion. Here the distance of the point mass from the center O is given by the radial coordinate r, while the azimuthal angle phi describes the instantaneous position of the body on its trajectory. A simple pendulum, which consists of a point mass m hanging from the string attached to the pivot point O, also performs a constrained motion. The pivot point O can be chosen as both the reference point of the motion and the origin of the polar coordinate system, where the x-axis points downward. The radial coordinate r of the point mass is equal to the length of the string, while the azimuthal angle phi describes the instantaneous position of the body on its trajectory. In both cases the constraint of the motion is given by the equation stating that the radial coordinate r describing the distance of the body from the point O is constant during the motion. The role of constraints is not only evident for moving objects, but constraints can also be applied in the description of bodies at rest where the forces acting on the body are in balance. For example, if a body is at rest on the table, then the weight g of the body pushes the table. The principle of the action and reaction states that the force minus g is exerted on the body by the table due to the deformation of the surface of the table. Although the deformation is very small, the force minus g produced by this deformation is obviously a force acting on the body. Therefore, the gravitational force g acting on the body is an unconstrained force, whereas the reaction minus g describes the effect of the constraint imposed by the surface of the table, and it is called constraint force. The net force F acting on the body vanishes, that is, F is equal to the action g plus the reaction minus g, which is equal to 0. As a result, the forces acting on the body are in balance and the body stays at rest. We already interpreted this force balance by stating that the table prevents the body from falling down, but we can also consider the body as a point mass under the influence of the net force F, which is equal to 0. Based on this example, we can see that the fundamental equation of dynamics has the following form for the constrained motion of a point mass m. The mass m times the acceleration a of the point mass is equal to the net force F acting on the body, which is given by the sum of the net force F0 of the unconstrained forces exerted on the body and the net force F' of constrained forces exerted on the body. Such a decomposition of the net force F is justified by the fact that the unconstrained forces acting on a body, such as weight, gravitational force, quasi-elastic force or the force of air resistance, are generally known from the laws of force, as opposed to the constrained forces acting on the body. It is the part of the tasks to determine the constrained forces in the system under study. Nevertheless, constrained forces can easily be determined from the constraints and the law of action and reaction in simple cases, since such forces are usually perpendicular to the given surfaces or curves representing the constraints. Let us illustrate these statements with some examples. In the first example, let us consider the forces acting on a body which is on a ramp with the angle alpha measured between the horizontal plane and the surface of the ramp. The weight g of the body is equal to the mass m of the body times the gravitational acceleration g, which points downward. We can decompose this force to the component Gn normal to the surface of the slope, and the component Gt tangent to the surface. That is, the weight g of the body is equal to the vector sum of the components Gn and Gt, as the parallelogram law applied for these forces shows in the figure. Then the magnitude of the normal component is given by the mass m times the magnitude of the gravitational acceleration g times cosine alpha, and the magnitude of the tangential component is equal to m times g times sine alpha. Since we neglect the friction between the body and the surface of the ramp, the tangential force Gt does not act on the ramp. However, the normal component Gn is exerted on the ramp, and as a reaction, the constrained force F' due to the deformation of its surface is also exerted on the body, where F' is equal to minus Gn. As a result, both the unconstrained force F0 given by the weight G, that is the gravitational force, and the constrained force F' act on the body. Then the net force F exerted on the body is equal to the sum of F0 and F', that is the weight G minus the normal component Gn. Since the weight G is decomposed to its normal and tangential components, the result is given by the tangential component Gt of the weight. That is, the net force F acting on the body points in the tangential direction and its magnitude is equal to the mass m times the magnitude of the gravitational acceleration g, times sine alpha. The fundamental equation of dynamics states that the force F exerted on the body is equal to its mass m times its acceleration a. By applying this equation, we can demonstrate that the body slides down the ramp, and its acceleration a is equal to the tangential component gt acting on the body, divided by its mass m. Then the acceleration of the body has also a tangential direction, and its magnitude is equal to the magnitude of the gravitational acceleration g, times sine alpha. This formula shows that the steeper the ramp is, the greater the acceleration of the body is. In a limiting case where alpha tends to 90 degrees, the acceleration of the body approaches the gravitational acceleration g, and we can talk about the free fall of the body along a vertical surface. For alpha equal to 0, the ramp becomes a horizontal surface and the body has no acceleration. Therefore, if the body was already at rest, then it stays at rest. If we perform the experiment, then we always measure smaller values for the magnitude of the acceleration of the body than g times sine alpha. Since the frictionless motion is an idealized model, the friction between a sliding body and the surface of the ramp reduces the magnitude of the acceleration of the body. Similarly, since bodies have extension and shape, in the case of rolling balls, the rotation of the ball also reduces the magnitude of its acceleration. However, the acceleration is still constant in both cases, and the body moving on a ramp performs a uniformly accelerating motion. As a result, the distance s covered by the body sliding on or rolling down the ramp under the influence of gravity is given by 1/2 times the magnitude of the acceleration a of the body, times the square of the time t measured during its motion. In other words, the distance s between the initial and the final positions of the body is directly proportional to the square of the elapsed time t. This fact was demonstrated by Galileo in his inclined plane experiment, as we discussed it in kinematics. We can also compensate the force Gt acting on the body in a setup, or we connect a cart to a weight with a string over a pulley and place it on a ramp, as seen in the figure. If the inclination angle alpha of the ramp can be adjusted, we can find an angle where the cart and the weight remain at rest. Then the tangential force Gt acting on the cart and the force minus Gt exerted on the cart by the string are in balance. Similarly, the force G' acting on the weight under the influence of gravity and the force minus G' exerted on the weight by the string are also in balance. In such a configuration, the magnitudes of the forces minus Gt and minus G' are equal, and given by the mass m of the cart times the magnitude of the gravitational acceleration g times sine alpha. This relationship shows that the inclination angle alpha of the ramp is uniquely determined by the mass m of the cart and the weight G'. In the next experiment, we connect a cart to a spring dynamometer or a spring scale with a string and place it on a table. We connect the other end of the scale to a weight with a string over a fixed pulley attached to the table, and suspend the weight from the spring, as seen in the figure. Let M1 and M2 denote the mass of the weight and the cart respectively. Then the weight G1 is given by the mass M1 times the gravitational acceleration g, and the weight G2 of the cart is equal to the mass M2 times the gravitational acceleration g. In this setup, the cart is held in the same position on the table so that the whole system is at rest. If the mass of the spring scale is much smaller than the total mass of the weight in the cart, the magnitude of the force F' exerted on the cart by the string is equal to the magnitude of the weight G1. Then the magnitude of the force F' is equal to the mass M1 of the weight times the magnitude of the gravitational acceleration g, which is measured by the spring scale. If we let the cart move, then it performs a uniformly accelerating motion, that is, the distance covered by the moving cart is directly proportional to the square of the time t measured from the beginning of its motion. In the moving system, the spring scale measures a force less than the mass m1 times the magnitude of the gravitational acceleration g. If the unconstrained forces g1 and g2 are known, we can determine both the motion of the bodies and the forces acting on them. The weight g2 of the card is a force exerted on the table which we consider as action, and the reaction minus g2 is exerted on the cart by the table. These forces compensate each other, and they do not accelerate the cart. The forces F' and minus g1 pulling the strings and the spring scale point to left and upward respectively, but they have the same magnitude. As a result, the magnitude of the net force acting on the weight is given by the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F', whereas the magnitude of the net force acting on the cart is equal to the magnitude of the force F'. If we suppose that the strained strings cannot be stretched, then they represent constraints in the system. These constraints imposed on the motion of the bodies results in the fact that the accelerations of the cart and the weight have the same magnitude. By applying the fundamental equation of dynamics for the two bodies, we can state that the mass m1 of the weight times the magnitude of the acceleration A is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F'. Similarly, the mass m2 of the cart times the magnitude of the acceleration A is equal to the magnitude of the force F'. The sum of these two equations gives the equation stating that the sum of m1 and m2 times A is equal to m1 times g. If we divide this equation by the sum of m1 and m2, we can express the magnitude of the acceleration of the two bodies as the fraction of the mass m1 to the sum of the mass m1 and the mass m2, times the magnitude of the gravitational acceleration g. We can substitute this result into the fundamental equations, and express the magnitude of the constrained force F' as the mass m1 times the magnitude of the gravitational acceleration g, times the quantity of 1 minus the ratio of m1 to the sum of m1 and m2, or as the ratio of m1 times m2 to the sum of m1 and m2, times the magnitude of the gravitational acceleration g. For example, if the mass of the weight hanging from the spring is equal to 0.2 kg and the mass of the cart is equal to 0.8 kg, then the force F' measured in the system at rest is given by the mass m2, that is 0.8 kg times the gravitational acceleration, that is 9.81 meter per second squared, which is equal to 7.848 Newton. In the moving system, the acceleration A is equal to the gravitational acceleration g divided by 5, or 1.96 meter per second squared. The force F' accelerating the cart is given by 4/5, times the mass m1 times the gravitational acceleration g, which is equal to 6.278 Newton. This result also demonstrates that the force measured by the spring scale in the moving system is smaller than the one measured in the system at rest. As in the case of the experiment with the ramp, the measured acceleration of the cart is about 5 to 10% smaller than the computed value where the friction and the rotation of the wheels of the cart are neglected. Although the experiment shows that the acceleration is equal to the ratio of the force given by m1 times the gravitational acceleration g to the sum of the mass m1 and the mass m2, it cannot be used as an illustration of the second law of motion for a point mass m1 plus m2. We obtained this result in a system of two bodies and strings, which cannot be approximated as a single point mass. In the next example, we present the basic experiment with an Atwood machine shown in the illustration. The apparatus consists of a pulley attached to a stand with the masses connected by a string that runs over the pulley. A length scale and a pendulum are also mounted on the stand to measure the distance covered by the moving masses and the elapsed time, respectively. A small weight called rider is placed on one of the masses hanging from the string, where the string is pulled through a hole on the rider. Let us denote the total mass suspended in the right-hand side of the pulley and the mass of the weight hanging in the left-hand side by m1 and m2, respectively. In this setup, the mass m1 is greater than the mass m2, and the weights g1 and g2 acting on both sides of the pulley are not balanced. As a result, the net force acting on the masses will accelerate the bodies in the vertical direction. Since the weight and the rider have the total mass m1, the gravitational force g1 is equal to m1 times the gravitational acceleration g. Similarly, the gravitational force g2 is given by the mass m2 of the weight times the gravitational acceleration g. Then the magnitude of the net force acting on the weight and the ride is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F' exerted by the string. Similarly, the magnitude of the net force acting on the weight in the left-hand side is given by the magnitude of the force F' exerted by the string, minus the mass m2 times the magnitude of the gravitational acceleration g. Here we assume that the mass of the pulley can be neglected and the string cannot be stretched. Therefore, the forces exerted by the string at both ends have the same magnitude. These forces can be substituted into the fundamental equation of dynamics applied for the weights hanging from the string. Then we can state that the mass m1 times the magnitude of the acceleration a of the system is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F prime. Similarly, we can state that the mass m2 times the magnitude of the acceleration a of the system is equal to the magnitude of the force F prime, minus the mass m2 times the magnitude of the gravitational acceleration g. The sum of these equations gives the equation stating that the sum of the masses m1 and m2 times the magnitude of the acceleration a is equal to the difference of the masses m1 and m2 times the gravitational acceleration g. We can express the magnitude of the acceleration a of the moving weights from this equation, as the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2, times the magnitude of the gravitational acceleration g. By substituting this result into the fundamental equations applied for the moving bodies, the magnitude of the constrained force F prime can be written as the mass m1 times the magnitude of the gravitational acceleration g, times the quantity of 1 minus the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2. Or the mass m2 times the magnitude of the gravitational acceleration g, times the quantity of 1 plus the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2. If we insert spring scales in the vertical parts of the strings, then we can measure the constrained force F prime, which is less than the weight g1 and greater than the weight g2. With the vertical length scale and the pendulum, we can measure the distance s covered by the moving bodies during a given time t. It also allows us to demonstrate that the motion has a uniform acceleration by testing the distance formula, which states that the covered distance s of the accelerating bodies is equal to their acceleration a divided by 2, times the square of the measured time t. We can also show that the speed v of the bodies is equal to their acceleration a times the time t. When the weight with the rider is released, it accelerates for a distance s till the rider is caught by a ring allowing the weight to pass. From that moment, the weights g1 are the same in both sides, and so are the forces F prime exerted by both the ends of the string. As a result, the net forces acting on the weights vanish, and the system moves at a constant speed v, which can be determined by measuring the elapsed time t prime for the motion through the distance s prime. Then the speed v of the bodies performing a uniform linear motion is equal to the ratio of the distance s prime to the time t prime, and the acceleration a in the first stage of the motion is given by the ratio of the speed v to the time t. If we know the distance s, the acceleration a and the time t, we can verify the distance formula by substituting their values into the formula. We have seen that the right-hand weight of the Atwood machine is lowered, and the left-hand weight is lifted while they were accelerated. Let us discuss this vertical acceleration of the masses suspended from the spring in both cases separately. We will consider a weight suspended from a string, where a spring scale is used to measure the force exerted on the mass by the string. First we lift a mass m with the acceleration a, as seen in the figure. Here the gravitational force g acting on the weight is given by the mass m times the gravitational acceleration g. If F denotes the force exerted on the mass by the string, then the net force acting on the body is equal to the vector sum of the force F and the weight g. We note that the acceleration of the mass points upward, that is, it has the same direction as the force F. Then the fundamental equation of dynamics applied for the body states that the mass m times the magnitude of the acceleration a is equal to the magnitude of the force F exerted on the body, minus the mass m times the magnitude of the gravitational acceleration g. Then we conclude that in order to lift a mass m with the acceleration a, we need to exert the force F on it, where the magnitude of the force is given by the mass m times the sum of the magnitudes of the gravitational acceleration g and the acceleration a of the body. That is, we exert a force on the body which is greater than the gravitational force acting on the body. In the second case, we study the lowering of the mass m with the acceleration a. Since the directions of the force F and the weight g acting on the body are the same as in the first case and the weight is accelerating downward, the acceleration a and the force F point in opposite directions. As a result, the fundamental equation of dynamics states that the mass m times the magnitude of the acceleration a is equal to the mass m times the magnitude of the gravitational acceleration g, minus the magnitude of the force F exerted on the body. Then the magnitude of the force F is given by the mass m times the difference between the magnitudes of the gravitational acceleration g and the acceleration a of the body. That is, we exert a force on the body which is smaller than the gravitational force acting on the body. In the case of uniform linear motion, the acceleration vanishes and the fundamental equation reduces the equation stating that the force exerted by the string on the body is equal to its mass m times the gravitational acceleration g. That is, the force F compensates the gravitational force and the net force exerted on the body vanishes. This phenomenon can also be demonstrated as follows. If we step on a body weighing machine and crouch down suddenly, then we decelerate our body downward, that is, we accelerate the mass of our body upward. As a result, the force F measured by the weighing machine is smaller than our weight given by the mass m of our body times the gravitational acceleration g. If we straighten while we are still standing on the weighing machine, then we accelerate our body downward, and the force F measured by the weighing machine is greater than our weight measured at rest. We will finish the series of examples presented here with another simple experiment where a stand is erected on the pan of a weighing scale, and a flywheel is suspended on it by winding a string around its axis. We can balance the mass m of the stand and the flywheel with some weight placed on the other pan of the scale. If the flywheel is completely wound up and held in that position, it will wind down after its release, and its acceleration a will point downward. As a result, the magnitude of the force F measured by the weighing scale is equal to the mass m times the difference of the magnitudes of the gravitational acceleration g and the acceleration a, which is smaller than the weight of the stand and the flywheel. When the flywheel has completely unwound all the string, it reverses the direction of its motion and starts to wind up, whereas its center has a decelerating motion upwards. That is, its acceleration a still points downward. Then the force F measured by the weighing scale is still the same, and its magnitude is equal to m times the difference of g and a. That is, the scale still measures a force smaller than the weight of the stand and the flywheel. In the discussion about constrained motion, we neglected the friction between moving bodies. The concept of friction comprises all the phenomena related to the relative displacement and the resistance of such a displacement along the surfaces of solid bodies in contact, while they are sliding or trying to slide across each other. We can classify these phenomena in many different ways, but here we will focus on two types of them: sliding or kinetic, and sticking or static friction. Sliding or kinetic friction describes the situation where a solid body slides on the surface of another one, and we talk about sticking or static friction when the surface of a body adheres to the surface of another one rather than slides against it. In such cases, the bodies in contact are at rest and can be set in motion with respect to each other by exerting a given amount of force on any of them, so that the resistance due to friction could be overcome. Let us start with the discussion of sliding friction. If we place a block on a table and push it with a given initial velocity v0 along the surface of the table, then the velocity of the moving block will decrease and the body stops at some point, where its velocity becomes zero. The decrease in its velocity v and the deceleration of the body, or its acceleration a pointing to the opposite direction of the velocity, are attributed to the frictional force exerted on the body by the surface of the table. Based on the second law of motion, this force is measured by the product of the mass of the body and its acceleration. The law can also be used to measure frictional force in a static force measurement, where we exert a given amount force F' on the body in the horizontal direction by connecting a weight to the body with a spring over a pulley attached to the table and suspending the weight. We can measure the force F' with a spring scale inserted between the block and the pulley. For a proper choice of the weight pulling the block will still remain at rest. By pushing the block on the table, we can set the body in motion. In the experiment, we will find that the block performs a uniform linear motion, that is, it moves at constant velocity or vanishing acceleration. The second law of motion tells us that the net force F acting on the body, given by the product of its mass m and its acceleration a, must vanish. Therefore another force is exerted on the body which has the same magnitude as the force F' but points in the opposite direction. This force is the frictional force exerted on the block while it is sliding on the surface of the table. Instead of the weight suspended from the string, we can also use an electric motor with its axis connected to the block via a spring scale such that we could move the block over the surface of the table. If we switch the motor on and operate it at a low rotation speed, then the string will be coiled up on the rotating axis. As a result, the string exerts the force F' on the body and drags it along the surface of the table at constant speed. The frictional force acting on the block can be measured by the spring scale, since this force is just the opposite of the force F' exerted by the string. In this setup, the result of the experiment depends on several parameters, and we can modify them to study their effect on the frictional force produced by the moving block. We can change the area of the contact surfaces between the block and the table by placing it with another face on the table that has different area. We can change the velocity of the sliding body by modifying the rotation speed of the electric motor. We can change the magnitude of the force applied on the body in the direction perpendicular to the contact surfaces by placing a weight on the block. Finally, by replacing a block with another one which is made of a different material, we can change the physical properties of the surfaces sliding against each other. Such a comprehensive experiment was performed by Coulomb, who used a spring-driven setup in his experiment. His findings on the quantitative relationship between the frictional force and these parameters are called Coulomb's law of friction. If we consider two bodies sliding against each other at a constant velocity v where the force n applied on the bodies points in the direction of the surface normal of the contact surfaces, then the law states the following about the frictional force exerted by the bodies on each other. The direction of the frictional force is opposite to the velocity v, describing the motion of the contact surfaces with respect to each other. The magnitude of the frictional force is directly proportional to the magnitude of the applied force n in the normal direction of the contact surfaces. The magnitude of the frictional force depends on neither the area of the contact surfaces nor the magnitude of the velocity of their relative motion. In mathematical terms, Coulomb's law of friction states that the frictional force produced by the sliding contact surfaces is equal to minus a proportionality constant mu times the magnitude of the normal force n, times the relative velocity v divided by its magnitude. Minus the normalized velocity provides the direction vector of the frictional force, and the proportionality factor mu is known as the coefficient of the sliding friction. In this table, this coefficient is given for some pairs of different materials. We can see that mu is equal to about 0.5 for wooden bodies sliding against each other, which means that the frictional force is about the half of the normal force acting between their contact surfaces. The coefficient of sliding friction is equal to about 0.1 for bodies made of steel when they are sliding against each other. That is, the frictional force is much smaller than the one produced for wooden surfaces for the same normal force. The friction between an ice lump and a steel surface is even smaller since the coefficient mu for this pair of materials is equal to 0.014. In the experiment studying the friction of the sliding block on the table, the block was dragged along at a constant speed, which means that the net forces acting on the body vanish. If the magnitude of the force F' pulling the body is not equal to the magnitude of the frictional force produced by the contact surfaces, then the body will perform an uniformly accelerated motion. In a special case, the pulling force vanishes, that is, if we push the block and reduce the force F' to 0, then the instantaneous velocity v of the sliding body is reduced to 0 by the frictional force exerted on it by the table. As a result, the block covers some distance during its deceleration and finally stops. We can apply the second law of motion to determine the magnitude of the acceleration a of the body, which is given by the ratio of the magnitude of the frictional force acting on the body to its mass m. We already determined the magnitude of the frictional force of the horizontal sliding as the coefficient of the sliding friction times the magnitude of the normal force acting on the body. Then the magnitude of the acceleration a is equal to the coefficient of the sliding friction mu, times the magnitude of the normal force n, divided by the mass m. Since the normal force n is equal to the weight of the body, we can write the magnitude of the acceleration as the ratio of mu times the mass m times the magnitude of the gravitational acceleration g, divided by the mass m. Then we obtain the coefficient of the sliding friction mu times the magnitude of the gravitational acceleration g. Therefore, the acceleration a and the velocity v of the sliding body point in the opposite directions, and the magnitude of the acceleration is given by the coefficient of the sliding friction mu times the magnitude of the gravitational acceleration g. As we expected, the body has a constant acceleration, or rather deceleration since its acceleration is negative, and the distance s covered by the decelerating body is equal to the magnitude of its initial velocity times the time t, minus 1/2 times the magnitude of the acceleration a, times the square of the time t. In the case of uniformly accelerated motion, the magnitude of the instantaneous velocity v of the body is given by the magnitude of its initial velocity v0, minus the magnitude of its acceleration a times the time t. When the instantaneous velocity of the body decreases to 0, a body stops. Then its stopping time can be calculated from the equation stating that 0 is equal to the magnitude of its initial velocity v0, minus the magnitude of its acceleration a times the stopping time. As a result, the stopping time of the decelerating body is given by the ratio of the magnitude of the initial velocity v0 to the magnitude of the acceleration a, that is the ratio of the magnitude of the initial velocity v0 to the product of the coefficient of the sliding friction mu and the magnitude of the gravitational acceleration g. By substituting this result into the distance formula, we can write the stopping distance as the square of v0 divided by a, minus 1 over 2 times a, times the square of v0 divided by a. This is equal to the square of v0 divided by 2 times a, that is, the stopping distance is given by the square of the initial velocity v0 divided by 2 times the coefficient of the sliding friction mu, times the magnitude of the gravitational acceleration g. We can also see that the stopping distance of the body is equal to 1 over 2 times the magnitude of its initial velocity v0, times the stopping time. As an illustration of this phenomenon, let us consider a simple example with a car of 1.5 metric tons, that is 1,500 kilograms traveling with a velocity of 36 km per hour, that is 10 meter per second. If the driver of the car steps on the brake pedals, then the vehicle will slide before it stops. Let the coefficient of the sliding friction mu between the tires and the dry asphalt be about 0.5. By substituting these values into the expression of the stopping time, we obtain about 2 seconds. For the given initial velocity of the car and its stopping time obtained here, the stopping distance of the vehicle will be about 10 meters. We can also study the frictional force produced by a body moving on a ramp under the influence of gravity. In the next experiment, a block with the mass m is sliding down a ramp with the inclination angle alpha. We have already seen that the weight g of the body can be decomposed to its tangential and normal components with respect to the inclination plane of the ramp. Here the magnitude of the normal component of the weight is equal to the mass m times the magnitude of the gravitational acceleration g, times cosine alpha. Similarly, the magnitude of the tangential component of the weight is given by m times g times sine alpha. The net force exerted on the body sliding down the ramp is the vector sum of the tangential component of the weight g and the frictional force, and these forces point in the opposite directions. The normal component of the weight is compensated by the force minus gn exerted on the block by the ramp. Coulomb's law of friction states that the magnitude of the frictional force exerted on the block is equal to the coefficient of the sliding friction mu, times the magnitude of the normal force n acting on the body. In this setup, the normal force is equal to the normal component of the weight g of the body, and we have the coefficient of the sliding friction mu, times the mass m times the magnitude of the gravitational acceleration g, times cosine alpha. Since the block slides down, the magnitude of the frictional force preventing the motion is less than the tangential component of the weight g. We can express the magnitude of the acceleration a of the sliding block from the fundamental law of dynamics as the difference between the magnitudes of the tangential component of the weight g and the frictional force acting on the body, divided by the mass m. By substituting the explicit form of the forces acting on the body, we obtain the quantity of the mass m times the magnitude of the gravitational acceleration g times sine alpha, minus mu times m times g times cosine alpha, divided by m. As a result, the magnitude of the acceleration of a body sliding down a ramp with the inclination angle alpha is given by the magnitude of the gravitational acceleration g, times the quantity of sine alpha minus the coefficient of the sliding friction mu times cosine alpha. A special case of the frictional motion on the ramp is when the acceleration of the body vanishes and the body slides down at a constant velocity. Then the expression in the parentheses of the acceleration vanishes, that is sine alpha 0 minus mu times cosine alpha 0 is equal to 0. In this expression, alpha 0 denotes the inclination angle, where the body has a uniform linear motion on the ramp. As a result, we can express mu as the tangent of the inclination angle alpha 0. Then we can measure the coefficient of the sliding friction for the given pair of materials by finding the inclination angle of the ramp, where the body performs a uniform linear motion under the influence of gravity. If the inclination angle alpha of the ramp can be adjusted, as seen in the figure, we can find an angle where the block slides at a constant velocity on a surface of a given material attached to the inclined plane of the ramp. By varying the material of the block and the surface, we can measure the corresponding inclination angles of the ramp for different pairs of materials in the case of uniform linear motion. For example, if the surfaces sliding against each other are made of steel, then the measured inclination angle alpha is equal to 6 degrees. The tangent of 6 degrees is equal to 0.11, which is the coefficient of the sliding friction between steel surfaces as already shown in a table. The second type of friction presented here is sticking or static friction, which can also be demonstrated with the experiment setup applied for sliding friction. Let's suppose that the block is at rest on the horizontal surface of the table, which is connected to the weight with a string over the pulley attached to the table. The block starts to slide on the surface only if the force F' exerted on the body in the direction parallel with the surface reaches a given threshold. If we gradually increase the force F' by increasing the mass m of the weight, we can find the threshold measured by the spring scale, where the body starts to slide over the table. In this experiment it can be demonstrated that the threshold for the force F' is greater than the force needed to keep the body in motion. If the force F' acting on the body is less than this threshold, then the body stays at rest. By applying the fundamental equation of dynamics, we can conclude that besides the force exerted on the body by the string, there must be another constrained force acting on the body with the same magnitude but opposite in direction. This type of force is called sticking frictional force acting between the contact surfaces of the block and the table. The sticking frictional force resists the force F' applied to the block, and the body remains at rest until this static frictional force is overcome by the dragging force F'. Static friction can also be described by Coulomb's law of friction stating the following. The sticking frictional force is independent from the area of the contact surfaces and directly proportional to the normal force and applied on the body, where the proportionality constant μ0 is called the coefficient of static friction. This coefficient depends on the material properties of the contact surfaces, and always greater than the coefficient of sliding friction for the same pair of materials. The table displays the coefficient of static friction for the same pairs of materials for which the coefficient of sliding friction was already shown. We can see that the coefficient μ0 is equal to 0.6 between bodies made of wood. This value is 0.15 between steel surfaces, and 0.027 between ice and steel. We can also study sticking friction between different materials on a ramp. If we mount a surface made of a given material to the inclined plane of a ramp and place a block with the mass m on the surface, then the weight g of the block can be decomposed to its normal and tangential components with respect to the inclination plane with the angle alpha. Due to the sticking frictional force, reaction is produced not only against the normal component Gn of the weight but also against its tangential component Gt, provided the tangential component of the weight is less than the sticking frictional force exerted on the body. That is, the magnitude of the tangential component of the weight given by the mass m times the magnitude of the gravitational acceleration g, times sine alpha is less than the magnitude of the sticking frictional force given by the coefficient of static friction μ0, times the magnitude of the normal component of the weight of the block. Then the right-hand side of the inequality can be written as μ0 times m times g times cosine alpha. If we increase the inclination angle of the ramp gradually from 0, the body starts to slide on the ramp at given angle alpha 0. Then the condition states that the tangent of this angle is equal to the coefficient of static friction μ0. Therefore, by finding the inclination angle alpha 0 for which the blocks start to slide down the ramp, we can determine this coefficient for arbitrary pairs of materials. We already discussed uniform circular motion in kinematics. Now we study the forces acting on bodies during their motion along a circular path. In order to examine any kind of motion in dynamics, we always choose an inertial frame of reference where the laws of motion are valid. If the experiments studying uniform circular motion of bodies are performed in a laboratory, then we can consider this laboratory as an inertial frame of reference with respect to which the motion is described. Let us consider a point mass m moving along a circle with the radius r at a constant speed v. The trajectory of the point-like body is a circle with respect to the inertial frame, where the center O of the circle can be chosen as the reference point. Then the position vector r of the body points from the center O of its circular path to its instantaneous position p, and the velocity v of the body is a tangent to the path at the point p with a constant magnitude. In kinematics, we demonstrated that the angular velocity omega of the point mass rotating around the center O is given by the ratio of the speed v to the radius r. We also saw that the acceleration of a body performing uniform circular motion is equal to minus the square of its angular velocity omega, times its position vector r. This means that the centripetal acceleration of the body always points in the direction of the center O. Since the second law of motion states that the force F acting on a body is equal to the mass m of the body times its acceleration a, the force related to the centripetal acceleration, known as the centripetal force exerted on the point mass, is given by minus the mass m times the square of the angular velocity omega, times the position vector r. By expressing the angular velocity in terms of the speed of the body, the force F can also be written as minus the mass m times the ratio of the square of the speed v to the radius r, times the position vector r divided by its length. The centripetal force is the net force acting on a body moving along a circle at a constant speed. Both expressions describing the force F show that it has a constant magnitude but always points in the direction of the center of the motion. Therefore, it is always perpendicular to the velocity v of the moving body. Due to this fact, the velocity is the tangent to the circle in every point along the path of the motion while its magnitude remains constant. The frequency nu and the period t introduced for periodic motions are given by the angular frequency omega divided by 2 pi, and 1 over nu, respectively. We can express the force exerted on a body in uniform circular motion in terms of these quantities as well. Since the magnitude of the centripetal force acting on the body is equal to its mass m times the ratio of the square of its speed v to the radius r of its circular path, it can be written as the mass m times the speed v times the angular frequency omega. If we express the speed as the radius times the angular frequency and substitute it into the right-hand side, then we see that the magnitude of the force is equal to m times omega squared times r. This result can already be written in terms of the frequency or the period. That is, we have 4 pi squared times the mass m times the square of the frequency nu times the radius r, or the mass m times the ratio of 4 pi squared to the square of the period t times the radius r. Therefore the centripetal force is inversely proportional to the radius of the circular path for a given speed of the point mass, and directly proportional to the radius for a given angular velocity, or equivalently for a given frequency or a given period of the motion. Here we present some simple examples to illustrate the centripetal forces produced in uniform circular motion. In the first example, we describe an experiment with a bicycle tire leaning on the floor. If we insert a small ball in the tire, then the body can roll along its internal surface. By pushing the ball along the surface, we can set it motion such that it rolls along a circle inside the tire. We can assume that the friction between the rolling ball and the tire is small enough that the ball approximated as a point mass could perform a uniform circular motion, at least for a short time. In other words, the magnitude of its velocity v is constant, whereas it always points in the direction of the tangent to the circular path at its instantaneous position. As a result, the ball has a centripetal acceleration a, since the centripetal force F is exerted on the moving body by the inner surface of the tire. At the same time, the ball also exerts the force minus F on the tire. We can remove some part of the tire and repeat the experiment. When the ball reaches the missing part of the tire, no centripetal force is exerted on it, and the net force acting on the body vanishes. Therefore its acceleration also vanishes, and the ball will perform a uniform linear motion in the direction of the tangent to the circle at the point where it reached the missing part. A similar effect can be seen in the case of the sparks emitted from a grinding stone. Once the sparks are produced, no external force acts on them and they keep their initial velocity. As a result, the direction of their motion cannot change and they follow paths tangential to the rotating stone. In the next example, a ball with a mass m is attached to a string and whirled in a circle by hand. While the ball is in motion, we can feel the centripetal force F pulling our hand, which points in the direction of the center of the circle. By keeping the end of the string in the same position, we apply the opposite of this force on the ball so that it could be held on its circular path. If we cut the string and the centripetal force ceases to act on the ball, then it moves in the direction tangential to the circle at its instantaneous position. In other words, the ball follows the direction of its instantaneous velocity at that point. The tension in the string is due to the centripetal force and its opposite force. If F max denotes the force at which the string breaks, then the second law of motion states that the magnitude of F max is equal to the mass m of the ball times the magnitude of its centripetal acceleration corresponding to this force. Here the centripetal acceleration is given by 4 pi squared, times the square of the maximum frequency of the rotation of the ball denoted by nu max, times the radius r of the circular path. Then we can express the maximum frequency of the rotation as 1 over 2 pi, times the square root of the ratio of the maximum force to the mass m times the radius r. The third example is the moon orbiting the Earth, where the centripetal force acting on the moon is equal to the gravitational force exerted on it by the Earth. The fourth law of motion, that is the law of action and reaction, states that if the centripetal force F is the action, then there is a reaction, that is an opposite force minus F to the centripetal force. This opposite force points outward along the radius of the circular orbit of the moon, and its magnitude is given by the mass m of the moon, times the square of its angular velocity omega, times the position vector r of the moon with the tail at the center of the Earth. However, this force is exerted not on the moon but on the Earth, which, in turn, exerts the centripetal force on the moon. This is the case in the first and the second examples as well, where the opposite force minus F acts on the bicycle tire or our hand, respectively. The opposite force to the centripetal force is also known as centrifugal force, but this term has other meanings in dynamics, and we only will use it when we study motion in a rotating frame of reference instead of a rest frame. In another example, we study the centripetal force produced in the motion of a conical pendulum. Such an apparatus is a simple pendulum, that is a point mass m suspended on a string with the length L, where the mass of the string can be neglected. However, in the case of a conical pendulum, the point mass moves along a horizontal circle with the radius r at a constant angular velocity omega, instead of moving in a vertical plane. As a result, the string used for the suspension moves along the curved surface of a cone with the base determined by the circle and with the vertex at the point of suspension. Then the radius r of the circular path is given by the length L times sine phi, where phi is the opening angle of the cone divided by 2. The gravitational force g acting on the point mass is equal to the mass m times the gravitational acceleration g, which is an unconstrained force. The constrained force F' is exerted on the point mass by the string, which is opposite to the component of the weight g parallel with the string. Then the net force F acting on the body, that is the vector sum of the weight g and the force F' points in the direction of the center O of the circular path of the body. The fundamental equation of dynamics states that the mass m of the body times its centripetal acceleration a is equal to the net force F acting on it. Then we can state that the mass m times the magnitude of the centripetal acceleration given by omega squared times the radius r of the circle is equal to the magnitude of the centripetal force F. Since we can obtain the magnitude of the force F from the trigonometric relation between F and the weight g, we write that the mass m times omega squared times the length L times sine phi is equal to the mass m times the magnitude of the gravitational acceleration g, times the tangent of the angle phi. If phi is not equal to 0, we can express cosine phi as the ratio of the magnitude of the gravitational acceleration g to the length L times the square of the angular velocity omega, or as the magnitude of the gravitational acceleration g divided by 4 pi squared times the length L times the square of the frequency nu. This formula shows that we can widen the opening angle of the conical surface swept out by the string, if we increase the angular velocity or the frequency of the circular motion of the body suspended from the string. The operation of a centrifugal or flyball governor is based on this effect. Such a device controls the speed of a steam engine by regulating the flow of the working substance through a throttle valve. As a result, the governor is able to maintain a near constant speed or rotational frequency within reasonably close limits regardless of the load. A typical governor consists of a pair of balls attached to a vertical spindle driven by the prime mover, where the weight g of the balls and the opposite force to its component in the direction parallel with the arms gives the centripetal force F. This force is used as a controlling force which keeps the balls rotating along a given circular path. With a decreasing load on the engine, the speed of the prime mover increases and the central spindle of the governor rotates at a faster rate. Then the controlling force is overcome and the balls move outward. The sleeve attached to the balls by linked arms will slide up the vertical spindle and reduce the aperture of the throttle valve. As a result, the rate of steam admitted to the engine is reduced, which also reduces the rotation speed of the spindle. An increase in the load will have the opposite effect, that is the balls of the governor rotating at slower rate move downward as the controlling force is weakened. Then the sleeve will slide down the spindle and increase the aperture of the throttle valve. In the last example we describe an experiment for the study of centripetal force versus the elastic force. The apparatus used in the experiment consists of a ball with a mass m which can move along a horizontal rod. The rod is mounted on the top of a vertical spindle with a spring coiled around it. The ball is attached to the spring with a string over a pulley, as seen in the figure. We choose the length of the string connecting the ball to the spring such that the ball is at the spindle when the apparatus is at rest. If the spindle is rotated, then the ball performs a uniform circular motion with the angular velocity omega. At the same time, it moves radially outward from the center of the motion covering the distance r. In other words, the ball moves along a circle with the radius r. Since the ball is connected to the spring, it will stretch the spring by exerting the force F on it, and as a reaction, the spring exerts the force F' on the ball. Hooke's law states that the magnitude of the elastic force produced by the spring is equal to the spring constant k times the displacement r of the spring. The condition of the uniform circular motion of the ball is that the magnitude of the centripetal force acting on it must be equal to the magnitude of the elastic force produced by the spring. That is, the mass m times the square of the angular velocity omega of the ball times the radius r is equal to the spring constant k times the displacement r. Then we can express the angular velocity omega from this equation as the square root of the ratio of the spring constant k to the mass m. This result shows that there is only one critical angular velocity or rotational frequency at which the ball can perform a uniform circular motion. Since this expression does not depend on the radius r of the circle, the ball can be at any position on the rod during its circular motion. If we modify the radius at the given critical angular velocity, then we will see that the ball will still perform a circular motion for an arbitrary radius. However, by changing the angular frequency, the ball starts to move along the rotating vertical rod. When we studied the motion of a point-like body along arbitrary curves, we described its kinematic quantities in a Serret-Frenet frame attached to the moving body. The curve describing the trajectory of the point-like body or the point mass m is given by the position vector r of the point mass with respect to any reference point, and it is a function of time or the arc length s measuring the distance covered by the body along the curve. The moving frame consists of the tangent t to the path of the point mass at its instantaneous position, the normal vector n pointing from the same position in the direction of the center of the osculating circle with the curvature radius rc, and the binormal vector b given by the cross product of the tangent t and the normal n. We demonstrated that the acceleration a of the body can be expressed as a linear combination of the tangent t and the normal n, that is, it can be decomposed in the tangential and the normal directions. The tangential component of the acceleration is directly proportional to the derivative of the speed v of the body with respect to the time, whereas its normal component, that is the centripetal acceleration of the body, is directly proportional to the ratio of the square of the speed v to the curvature radius rc. If we apply the fundamental equation of dynamics stating that the net force F acting on a body is equal to the mass m of the body times its acceleration a, we can write the net force F as the vector sum of its tangential and normal components. We call these components tangential force and centripetal force, respectively. The tangential force acting on the body is given by the mass m of the body times the tangential component of the acceleration a, which is equal to the mass m times the derivative of the speed v with respect to the time, times the tangent t. Since the derivative of the arc length with respect to the time is equal to the speed, we can write that the tangential force is given by the mass m times the second order derivative of the arc length s with respect to the time, times the tangent t. Similarly, the centripetal force acting on the body is given by the mass m of the body times the centripetal acceleration, which is equal to the mass m times the ratio of the square of the velocity v to the curvature radius rc, times the normal n. If the body moves along a line, then the curvature radius rc of the osculating circle is infinity along the linear path of the body. As a result, the normal component of the force, or the centripetal force acting on the body, vanishes, and only the tangential force will accelerate the body along the line. In the case of uniform motion, where the speed of the body is constant, the tangential component of the force acting on the body vanishes, and only the centripetal force will accelerate the body, keeping it on a circular trajectory. In the example of a ball rolling in a bicycle tire, we neglected the friction between the ball and the tire. However, if the ball is set in motion along the internal surface of the tire, then the magnitude of its velocity is reduced by the frictional force pointing in the tangential direction of the motion, whereas the centripetal force is exerted on the ball by the surface of the tire. When we whirl a ball attached to a string, we can perform the experiment by circling our hand. Then the net force F acting on the ball is given by the vector sum of the centripetal force and the tangential force exerted on the body by the string. We denote the tangential force by the subscript 1, indicating that the net tangential force acting on the body can be different. If we does not neglect the frictional force denoted by the subscript 2 exerted on the moving ball in the air, we can write the net tangential force as the vector sum of the tangential force exerted on the body by the string and the frictional force pointing in the opposite direction. If the net tangential force vanishes, then the ball will perform a uniform circular motion. This example also demonstrates that the tangential and centripetal forces belong to the already known types of forces, such as the gravitational, elastic and muscular forces, and do not represent a new type of force. However, the tangential force is an unconstrained force, while the centripetal force can be both an constrained and unconstrained force. In most cases, the centripetal force is a constrained one, as seen in the example. We can also see that these forces do not represent a new type of force because the component equations of the net force F exerted on a body moving along a curve do not describe a law of force. They are just special forms of the fundamental equation of dynamics. If the motion of the body is known, that is, the kinematic quantities describing its motion are given, then the tangential and centripetal forces acting on the body can be determined from these expressions. If our goal is to determine the trajectory, the velocity and the acceleration of the body as a function of time, then these expressions, which are the differential equations of the kinematic quantities, can be solved for these variables. We can also decompose the net force F exerted on the body in the moving frame. Then the components of the fundamental equation of dynamics in the Frenet-Serret frame attached to the moving body are its equations of motion, which are the following. The tangential component states that the mass m of the body times the second-order derivative of the arc length s covered by the body with respect to the time is equal to the tangential component of the force acting on the body. The normal component states that the mass m times the square of the velocity v divided by the curvature radius rc is equal to the magnitude of the centripetal force acting on the body. Since the binormal component of the acceleration vanishes, the binormal component of the force F acting on the body vanishes as well. We can also express the net force F as the sum of the unconstrained force F0 and the constrained force F'. If we decompose both the unconstrained force and the constrained force exerted on the body in the moving frame, then we can express the force terms in the equations of motion as follows. The normal and binormal components of the force F generally consist of the components of both the unconstrained force F0 and the constrained force F' acting on the body, while the tangential component of the constrained force normally vanishes and does not have a contribution to the tangential component of the force F, as we mentioned earlier. The unconstrained force F0 is known, that is, its components in the moving frame are given as functions of time, whereas the non-vanishing components of the constrained force F' are unknown. The arc length s covered by the moving body along its trajectory can be obtained by solving the tangential component of the equations of motion. If we know the trajectory of the moving body, then we can determine all the kinematic variables describing its motion. By substituting them into the normal component of the equations of motion, we will be able to solve them for the corresponding components of the constrained force F' in the moving frame. That is, we can determine the constrained force F' as a function of time. Now, we will study the motion of a simple apparatus called mathematical pendulum operating under the influence of gravity. Mathematical pendulum is an idealized model of simple pendulums. A simple pendulum consists of a small bob suspended by a string or a rod from a rigid support or the ceiling, as seen in the photo. We will approximate the simple pendulum with its mathematical model, where a point-like bob or point mass m is suspended from the fixed point P with a string of the length L. The string has a negligible mass and cannot be stretched, and we will also neglect the drag force acting on the moving bob due to the air resistance. Then there is only one unconstrained force acting on the point mass, which is the gravitational force given by the mass m times the gravitational acceleration g. The constrained force F' exerted on the point mass by the string or the rod is the opposite force to the weight of the point-like bob. If the pendulum is at rest, the string or rod is in a vertical position and the bob hangs at the end of the suspension in equilibrium. When the bob is displaced from its equilibrium position and then released, the net force given by the vector sum of the gravitational force g and the constrained force F' accelerates the body in the direction of the equilibrium position. As a result, the bob will swing back and forth around its equilibrium position along an arc between its turning points. In other words, the point mass in the idealized model starts a periodic motion or oscillation in a vertical plane. Therefore, the motion of the pendulum is planar motion, and the pendulum is also called planar pendulum, where the whole suspension string or rod moves along the vertical plane determined by the initial velocity of the bob. However, we can talk about other types of pendulum in terms of the initial velocity of the bob. We perform experiments with a conical pendulum. If we push the bob displaced from its equilibrium position such that its initial velocity is perpendicular to the plane determined by the equilibrium position and the displacement of the bob. As a result, the trajectory of the bob will be a circle in the horizontal plane determined by its initial position, and the string or rod moves along the conical surface with the apex determined by the suspension point P and the base determined by the circular path of the bob. In the general case, the initial velocity of the bob is not perpendicular to the plane determined by the equilibrium position and the initial displacement of the bob, and its trajectory can be a complicated curve on the spherical surface determined by the length of the suspension string or rod. A pendulum performing such a motion is known as spherical pendulum. Here we only study the motion of the planar pendulum depicted in the figure. The instantaneous position of the point mass m representing the bob can be described by the angle phi between the vertical line PO and the suspension string of the point mass. The point P is the point of the suspension and the point O denotes the equilibrium position of the pendulum. The length of the suspension string is denoted by L. The instantaneous displacement of the mathematical pendulum is given by the angle phi, which is measured counterclockwise. Then the arc length s covered by the moving bob from the point O is positive to the right of the equilibrium position and negative to the left of the point O, and it can be written as the length L times the angle phi where the angle is measured in radians. The only unconstrained force acting on the moving point mass is the gravitational force given by the mass m times the gravitational acceleration g. We can decompose the weight g to the components tangential and perpendicular to the path of the motion. The magnitude of the tangential component can be written as the mass m times the magnitude of the gravitational acceleration g times sine phi, whereas the magnitude of the normal component is given by m times g times cosine phi. The constrained force F' is exerted on the point mass by the suspension string, where F' and the normal component of the weight g have opposite directions. As already mentioned, we neglect the frictional force acting on the moving mass point. Then the net force F acting on the point mass is the vector sum of the weight g and the force F'. Now we can apply the fundamental equation of dynamics stating that the net force F acting on the point mass m is equal to the mass m times the acceleration a of the point mass. The equations of motion of the bob traveling along the arc are the components of the fundamental equation of dynamics. For the tangential direction we can write that the mass m times the magnitude of the tangential component of the acceleration a is equal to the magnitude of the tangential component of the net force F, which is equal to minus the magnitude of the tangential component of the weight g. The minus sign indicates that the tangential component of the weight g points in the opposite direction to the tangent to the path of the bob moving from its equilibrium position O to its turning point in the right-hand side. Similarly, for the normal direction we can write that the mass m times the magnitude of the centripetal acceleration is equal to the magnitude of the normal component of the net force F, which is equal to minus the magnitude of the normal component of the weight g, plus the magnitude of the force F'. The minus sign in the front of Gn indicates that the normal component of the weight g points in the opposite direction to the normal to the trajectory of the bob. In the discussion on the motion of a point-like body along an arbitrary curve we determine the tangential and normal components of its acceleration. We saw that the magnitude of its tangential component is given by the second-order derivative of the arc length s covered by the body with respect to the time t, whereas the magnitude of its centripetal acceleration can be written as the square of the speed v of the body divided by the curvature radius measured for the path of the body at its instantaneous position, which is equal to the length L in the case of the bob moving along an arc with the radius L. By substituting the components of the acceleration of the point mass and the force acting on it, we obtain the equations of motion of the pendulum, which are the following. In the tangential direction, the mass m times the second-order derivative of the arc length s with respect to the time t is equal to minus the mass m, times the magnitude of the gravitational acceleration g, times sine phi. In the normal direction, the mass m times the square of the speed v divided by the length L is equal to the magnitude of the force F', minus m times g times cosine phi. Since the arc length s covered by the moving bob is equal to the length L times the angle phi, the tangential component states that the second-order derivative of the angle phi is equal to minus the ratio of g to L times sine phi. We can use the normal component to compute the magnitude of the force F' acting on the bob if we already determined its speed v at the instantaneous position for a given angle phi. We only need to solve the differential equation describing the tangential component of the fundamental equation of dynamics. The differential equation can be written in the form stating that the second-order derivative of the angle phi measuring the deviation of the pendulum from its equilibrium position with respect to the time t, plus omega squared times sine phi is equal to 0. Here the constant omega is defined by the square root of the magnitude of the gravitational acceleration g divided by the length L of the suspension string of the pendulum. This is the final form of the equation of motion of the mathematical pendulum, and we see that it depends only on the parameter omega whereas it is independent of the mass m of the bob. If we assume that the pendulum swings through a small angle, that is the maximum of the angle phi is small, then we can approximate the sign of the angle with phi itself in the first order. As a result, the second term in the left-hand side of the equation of motion reduces to omega squared times phi, and we obtain the equation of motion for a harmonic oscillator. The solution to the oscillator equation states that the instantaneous displacement of the mathematical pendulum measured by the angle phi is equal to the initial angle phi 0 at the turning point, times the sine of the sum of omega times the time t and an initial phase shift angle alpha. In other words, the bob performs a simple harmonic motion for small swings, where the parameter omega is the angular frequency of the periodic motion. Then the period t of the oscillation is given by 2 pi times the square root of the length L of the suspension string divided by the magnitude of the gravitational acceleration g. Let us solve the equation of motion for the mathematical pendulum in the general case, and consider the original equation stating that the second-order derivative of the angle phi with respect to the time t plus omega squared times sine phi is equal to 0. The parameter omega squared is given by the ratio of the magnitude of the gravitational acceleration g to the length L of the suspension string. First, we cast this equation in a more convenient form by introducing a new variable. We will denote the first-order derivative of phi with respect to the time t by the function psi. Then the second-order derivative of phi with respect to the time t can be written as the derivative of psi with respect to the time t. Now we consider psi as a function of the function phi, and we apply the chain rule for the derivative. This gives the product of the derivative of psi with respect to the angle phi and the derivative of phi with respect to the time t, where we can substitute psi into the time derivative. In fact, this expression is equal to 1 over 2 times the derivative of psi squared with respect to the angle phi. Then we can write the equation of motion as a first-order differential equation stating that 1 over 2 times the derivative of psi squared with respect to the angle phi plus omega squared times sine phi is equal to 0. By separating its variables, we can integrate the differential equation, and express the function psi squared as 2 times omega squared times cosine phi, plus a constant of integration written as 2 times c. If we take the square root of both sides of the equation and substitute the definition of psi on the left-hand side, then the equation of motion can be written in the following form. The derivative of the angle phi with respect to the time t is equal to plus or minus the square root of 2 times the sum of omega squared times cosine phi and c. We have still a first-order differential equation, where the sign in the right-hand side of the equation can be determined by solving an initial value problem for the equation of motion. Without loss of generality, we will impose the following initial value condition on the solution to this differential equation. If the initial position of the pendulum is at any of its turning point, then the initial angle phi is equal to the minimum or the maximum angle phi 0, where the speed of the bob vanishes, that is its angular velocity given by the derivative of the angle phi with respect to the time t is equal to t0. Then the left-hand side of the differential equation vanishes if the time t is equal to t0. The right-hand side of the equation only vanishes if the constant of integration c is equal to minus omega squared times the cosine of the initial angle phi 0. Now we can substitute the constant c back into the differential equation, separate its variables and integrate it over an interval measured from the initial time t0 and the initial angle phi 0. As a result, we can write that the time t measured from the initial time is equal to plus or minus 1 over omega, time the integral of 1 over the square root of 2 times the difference between the cosine of the angle phi and the cosine of the initial angle phi 0 with respect to phi from phi 0 to the angle phi measured at the time t. By applying some trigonometric relations, we can write cosine phi as 1 minus 2 times the square of the sine of phi over 2. Similarly, we can write minus cosine phi 0 as minus 1 plus 2 times the square of the sine of phi 0 over 2. Then cosine phi minus cosine phi 0 can be written as 2 times the square of the sine of phi 0 over 2, minus 2 times the square of the sine of phi over 2. If we substitute this result into the integral, then the equation of motion of the pendulum has the following form. The elapsed time t is equal to plus or minus 1 over 2 times omega, times the integral of 1 over the square root of the difference between the square of sine phi 0 over 2 and the square of sine phi over 2 with respect to the angle phi, from the angle phi 0 to the angle phi measured at the time t. If the angle phi 0 is measured at the turning point in the left-hand side to the equilibrium position of the pendulum, then phi 0 is negative and represents the minimum angle of the swing of the pendulum. Therefore, the angle phi increases while phi 0 is always less than phi, and we choose the positive sign in the right-hand side of the equation. If the angle phi 0 belongs to the turning point in the right-hand side, that is phi 0 is the maximum angle of the swing, then the angle phi decreases and phi 0 is always greater than phi. In this case, we choose the negative sign in the right-hand side of the equation. This equation provides an implicit relationship between the elapsed time t and the angle phi determining the instantaneous position of the pendulum at the time t. The parameters of the equation are the minimum or the maximum angle phi 0 at the turning points, and the constant omega depending on the gravitational field at the place of the pendulum and the length of the suspension string of the pendulum. In order to transform the equation of motion into a more convenient form, we will change the variable of the integral in its right-hand side. Let us denote the sine of phi 0 over 2 by the letter k, and introduce the new variable theta with the condition k times sine theta is equal to the sine of phi over 2. In the initial position of the pendulum, where the angle phi is equal to phi 0, k times sine theta is equal to the sine of phi 0 over 2, which is equal to k by definition. Then sine theta must be equal to 1. As a result, in the initial position of the pendulum with the initial angle phi 0, the variable theta is equal to pi over 2. If we compute the differential of the equation used in the definition of theta, then we can state that k times cosine theta times the differential of theta is equal to 1 over 2 times the cosine of phi over 2 times the differential of phi. Here we can write the cosine of phi over 2 as the square root of 1 minus the square of the sine of phi over 2. If we substitute the definition of theta into the result, then we obtain 1 over 2 times the square root of the difference between 1 and k squared times the square of sine theta times d theta. We can express the differential of the angle phi from this equation as the ratio of 2 times k times cosine theta to the square root of the difference between 1 and k squared times the square of sine theta times d theta. We will use this equation to change the variable in the integral of the equation of motion of the pendulum. We saw that this equation states that the elapsed time t is equal to minus 1 over 2 times omega times the integral of the square root of the difference between the square of sine phi 0 over 2 and the square of sine phi over 2 with respect to the angle phi from the initial angle phi 0 to the angle phi measured at the time t. The minus sign in the right-hand side of the equation indicates that the turning point of the pendulum in the right-hand side was chosen as its initial position, and the angle phi decreases from phi 0 to minus phi 0 in the first half of the period of the motion. If we substitute the parameter k and the variable theta into the integrand, then we can write the time t as 1 over 2 times omega, times the integral of 1 over the square root of the difference between k squared and k squared times the square of sine theta, with respect to the angle phi from phi to phi 0. Here we absorb the negative sign into the integral by exchanging its limits. The integrand can be written as 1 over k times the square root of 1 minus the square of sine theta, which is multiplied by the ratio of 2 times k times cosine theta to the square root of 1 minus k squared times the square of sine theta, due to the change of the variable of integration, and the integration is performed with respect to the variable theta from a given theta to pi over 2. After simplifying the equation, we obtain the final form of the equation of motion, stating that the elapsed time t is equal to 1 over omega, times the integral of 1 over the square root of 1 minus k squared times the square of sine theta, with respect to theta from theta measured at the time t to pi over 2. Since the integral in the equation of motion cannot be evaluated analytically, we will only derive an expression for the period of motion of the pendulum in terms of its initial condition and the parameter omega. We chose the turning point of swings as the initial position of the pendulum. Then the bob will cover 1/4 of the path of its periodic motion when it passes through the equilibrium position. Therefore, it takes 1/4 of the period of its motion to reach the equilibrium position from the turning point. As already seen, theta is equal to pi over 2 for the initial angle phi 0. In the equilibrium position, the angle phi is equal to 0, which corresponds to a vanishing theta. Then the period t of the oscillation of the pendulum can be written as 4 over omega times the integral of 1 over the square root of 1 minus k squared times the square of sine theta, with respect to theta from 0 to pi over 2. In fact, we can recognize the integral in the expression obtained for the period of the swings of the pendulum. The integral of 1 over the square root of 1 minus k squared times the square of sine theta with respect to theta from 0 to pi over 2, is known as the complete elliptic integral of the first kind, denoted by the capital letter K. Since it is a definite integral, it only depends on the modulus k defined over the interval between 0 and 1. Then the period t of the motion of the mathematical pendulum is equal to 4 over omega times the complete elliptic integral of the first kind, where omega is defined by the square root of the magnitude of the gravitational acceleration g over the length L of the suspension string of the pendulum, and the modulus k is defined by the sine of the angle phi 0 describing the initial position of the pendulum over 2. If the pendulum with a suspension string of a fixed length is installed in a given place with a given gravitational acceleration, then the parameter omega is a constant and the only free parameter is the modulus k, that is the initial angle phi 0. This parameter will determine the period t for a given omega. Here we can see the complete elliptic integral of the first kind as a function of the parameter k. The graph shows that the integral is equal to pi over 2 if k vanishes, and diverges if k tends to 1. The table also demonstrates that the change in the value of the integral is more sensitive in the range close to 1, that is when the initial angle phi 0 is close to the straight angle. Although the elliptic integral of the first kind cannot be expressed in terms of elementary functions, it can be presented as an infinite series. The infinite series of this integral is the sum from n equals 1 to infinity of the square of a fraction times k raised to 2 times n, where the fraction is given by the factorial of 2 times n, divided by 2 raised to 2 times n, times the square of n factorial. This expansion allows us to approximate the period of the motion of the mathematical pendulum with an arbitrary precision. If this infinite series is substituted into the original equation, then the period t can be expressed as 2 pi over the parameter omega times a polynomial of the modulus k with infinite number of terms. We have seen that the pendulum performs simple harmonic motion for small swings with the angular frequency omega. In this case the modulus k tends to 0, and the period t of the motion reduces to the 0th order of the infinite sum, which gives 2 times pi divided by the angular frequency omega. By denoting the period of the oscillation of the pendulum for small swings by t0, we can see that the period t of arbitrary swings is always greater than the period t0 of the small oscillations of the pendulum, and t approaches t0 as the modulus k, or the initial angle phi0 tends to 0. This is illustrated in the following table where we show the ratio of the period t to the period t0 for different values of the initial angle phi0. For a vanishing initial angle, t and t0 are equal, and the deviation of the period t from the period t0 increases with the increasing angle phi0. The ratio of the periods can only be measured in par per thousand, if phi0 is equal to 10 degrees. However, its value raises to 1 700 for 60 degrees. If the initial angle of the pendulum is set to 120 degrees, the deviation is 10 times greater than the value obtained for 60 degrees. Although the initial angle phi0 is normally much smaller than 120 degrees, even smaller deviations in the period can be accumulated during several swings. Such a deviation will result in inconsiderable error in time measurements performed with mathematical or simple pendulums. Therefore, it is always important to apply the formula with infinite expansion of the elliptic integral to determine the period t of the motion of the pendulum with sufficient accuracy. When we observe the motion of planets and stars in the night sky, Earth serves for us as a frame of reference to describe the instantaneous positions of the celestial bodies. However, our planet also performs a complicated motion. Earth rotates about its axis once every 24 hours, while it revolves around the Sun with a varying velocity along an elliptical path. Furthermore, Earth possesses an axis of rotation that is not perpendicular to the plane of its elliptical trajectory, and has an angle of inclination that undergoes a precession with a period of 26,000 years. As a result, the description of the apparent motion of the celestial bodies is also complicated in this rotating and revolving frame of reference. It was therefore a great challenge for the astronomers in ancient times to construct a cosmological model providing a satisfactory description of celestial motion. Philolaus, a follower of the Pythagorean school in Greece, developed an astronomical system with the planet Earth rotating about its axis, while it revolves around a central fire distinct from the Sun, which also orbits the central fire. Thus the central fire is at the center of Philolaus' cosmos. The Sun and the planets move in perfect circles at constant angular velocity, executing the ideal form of motion. As already mentioned in the discussion on Aristotelian physics, the expectation of the ancient Greek astronomers was that celestial bodies must perform a uniform circular motion. In the Pythagorean cosmology, the motion of the stars and planets along circular paths representing a perfect geometric shape indicated the divine nature of the celestial objects. Aristotle also noticed that a counter-Earth was also introduced by Pythagoreans in order to bring the total number of the planets and the Sun orbiting the central fire up to the perfect number 10. Another Greek philosopher and astronomer, Heraclides Pontius, modified Philolaus' system by creating a geocentric worldview with the assumption that Earth is at the center of the universe. In his cosmology, our planet is at rest, whereas the Moon, the Sun and the outer planets revolve around Earth. Only the inner planets, that is Mercury and Venus, revolve around the Sun. Nevertheless, all the planets and the Sun has circular orbits and they move at constant speed along their paths. The most mature version of the geocentric cosmology is called Ptolemaic system after Ptolemy, an Alexandrian astronomer and mathematician. His model became a predominant description of the universe from antiquity and remained unchallenged till the beginning of Renaissance. The geocentric model assumes that the Earth is at rest and the center of the universe, and the Sun, the Moon and all the planets and stars revolve around the Earth. Although the Sun and the Moon move in circular orbits around the Earth, planets perform a composite motion in the geocentric model. They revolve around small circles, called epicycles, whose center C move along bigger circles, known as deferents. The center O of the deferents is called eccentric and it is at a given distance from the Earth. A planet performs uniform circular motion along its epicycle, and the same time the midpoints of the same epicycle moves along its deferent at a constant speed. This combined motion could explain the observations that the trajectories of planets appear loops in the sky where they have a retrograde motion. However, the geocentric model became more complicated with the improvement of the observational data, since in its original form it could not predict the observed size of the planet's retrograde loops. Ptolemy introduced the equant point E placed directly opposite to the Earth from the eccentric of each planet. He supposed that the center of the epicycle moves at a constant angular velocity with respect to the equant, which would produce a uniform circular motion. The improvement using the concept of equants was a deviation from the Pythagorean idea of perfect motion in the celestial spheres, and Nicholas Copernicus saw it as an aesthetic shortcoming which indicated the internal contradictions in the Ptolemaic system. The combination of different types of circular motion based on epicycles, deferents and equants became complicated, and it seemed to be a more straightforward way to interpret the planetary motion in a system with the Sun at the center. In his heliocentric cosmological model, Copernicus claimed that the planets including the Earth revolve around the Sun located at the center of the universe. Furthermore, each planet rotates around its axis, while orbiting the Sun. Then we can describe the motion of planets in a frame of reference attached to the Sun, and we can choose any coordinate system with the origin at the center of the Sun and the axes directed towards the fixed stars in the sky. Giordano Bruno claimed that Copernicus' heliocentric hypothesis was more than a mere mathematical formalism interpreting planetary motion. His model disproved not only Ptolemy's model but also the Aristotelian picture of the cosmos. According to Bruno, the heliocentric worldview completely rejects the fundamental idea of the peripatetic physics stating that the elements had the natural place at the center of the cosmos in the sublunary region. Bruno denied the existence of the celestial and sublunar spheres, indicating that the same laws of physics must be applied throughout the cosmos. Furthermore, Bruno also claimed that the universe is infinite and populated an infinite number of solar systems. This hypothesis goes far beyond the principle of heliocentric worldview, stating that there is no center in the universe at all. Tycho Brahe, a Danish astronomer, also admired Copernicus' work and tried to confirm his theory by studying the trajectories of objects in the sky. He performed the most precise observation of celestial motion before the invention of the telescope by applying a brass azimuthal quadrant seen in the figure. However, his observations did not prove the existence of the annual parallax of stars, which should be the result of Earth's motion around the Sun. Instead of abandoning the idea of the Earth located at the center of the cosmos, he constructed a geo-heliocentric system combining the immovable Earth with Copernicus' heliocentric geometry. In his cosmology, the Sun revolves around the Earth, whereas the inner planets orbit the Sun, providing a picture similar to Heraclides' astronomical model. His assistant, Johannes Kepler, already accepted the Copernican system. When he analyzed Brahe's observational data on Mars, Kepler applied the mathematical tools developed by Ptolemy to explain the observed motion in the heliocentric worldview. By assuming that the Sun does not move while Mars orbits the Sun, he tried to fit the parameters describing the geometric model with the observational data as much as possible. As a result, he discovered the laws of planetary motion breaking with the heritage of the Pythagorean cosmology, where planetary motion was explained as a composition of uniform circular motions. Let us study the three laws of planetary motion discovered by Kepler. These laws describe the motion of the celestial objects around the Sun with the point mass approximation, where the diameter of any orbiting planet is much smaller than the size of its orbit. Kepler's first law is called the law of orbits, and states that planets move in elliptical orbits with the Sun at one of the two foci. In other words, the planets in the solar system perform an elliptic motion while orbiting the Sun. As we have already seen in the discussion on elliptic motion of a point mass in kinematics, the elliptic orbit has a few parameters describing its basic properties. The shape of an ellipse is given by its major semi-axis A and minor semi-axis B, whereas its position is fixed by the locations of its foci F1 and F2. The eccentricity E of the elliptic orbit is also used to describe the shape of the orbit, which can be written as the square of 1 minus the ratio of B squared to A squared. The instantaneous position of the planet is described by the position vector pointing from either the focal point F1 or the focal point F2 to the position of the planet moving along the ellipse. If the Sun is at the focal point F1, then the reference point is F1. If the Sun is at the focal point F2, then we chose F2 as a reference point. The magnitude of the position vector gives the instantaneous distance of the planet from the Sun. In kinematics, we also derive the polar equation describing the instantaneous position of a point mass on an ellipse. If theta is the polar angle measured between the major axis of the ellipse and the position vector of the point mass, then the polar equation states that the distance r of the point mass from the reference point is given by the semi-major axis A times 1 minus the square of the eccentricity E, divided by 1 minus or plus e times the cosine of the polar angle theta. In other words, the instantaneous distance of the planet from the Sun is uniquely determined by the polar angle describing the direction of the position of the planet with respect to the major axis of its elliptical orbit. The sign in the polar equation is determined by the choice of the reference point. If the Sun is at the focal point f1, then we take the minus sign. If the Sun is at the focal point f2, then the plus sign is used in the denominator. Kepler's second law is known as the law of equal areas, and states that the position or the radius vector pointing from the Sun to any planet sweeps out equal areas during equal intervals of time. This law can be illustrated as follows. The position vector of the planet at a given time t1, and the position vector at the time t1 plus delta t determine the area delta A swept out by the moving position vector during the time interval delta t. Similarly, the position vector at the time t2 pointing to another position in the orbit of the planet and the position vector at the time t2 plus delta t also determine the area delta A swept out by the moving position vector during the time interval delta t. Since the time interval delta t is the same in both cases, the area swept out by the position vector are the same. As a result, it is not the instantaneous velocity v of the planet that is constant along its elliptic orbit but its areal velocity. When we studied the elliptic motion of a point mass with a constant areal velocity defined by the derivative of the area A with respect to the time t, we showed that the areal velocity of the moving body can be written as 1 over 2 times the cross product of its position vector r and its velocity v. Kepler's law states that the vector of the areal velocity is constant. The first law also tells us that the orbital motion of the planets is a planar motion, and the position vector of the planet and its velocity, that is the tangent to the elliptic orbit at the instantaneous position of the planet, remain in the plane of the motion. Then the direction of the areal velocity of the planet is perpendicular to the plane of the motion, and the second law states that its magnitude is constant during the periodic motion of the planet. We also derive the magnitude of the areal velocity in kinematics, and we can write that 1 over 2 times the square of the distance r of the planet from the Sun, times the derivative of its polar angle theta with respect to the time t is constant. It follows therefore that the instantaneous velocity of the planet has a maximum at the perihelion of its orbit, that is at the point nearest to the Sun of the planet in the path of the orbiting celestial body. Similarly, the planet has the minimum velocity at the aphelion, that is at the point farthest to the Sun of the planet in the path of the orbiting celestial body. Kepler's third law is called the law of periods, and states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of the semi-major axes of the elliptic orbits. If the semi-major axis and the period of the elliptic orbit of a given planet are denoted by A1 and T1 respectively, and A2 and T2 are the semi-major axis and the period of orbit of another planet in the solar system, we can write that the ratio of T1 squared to T2 squared is equal to the ratio of the cube of A1 to the cube of A2. In general, we can state that the square of the period Ti of the planet with the index I divided by the cube of the semi-major axis Ai of the orbit of the given planet is constant. In other words, the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their elliptic orbits, and the third law simply tells us that the proportionality constant is the same for each planet. Now we will give an overview of the fundamental parameters describing the planetary orbits in the solar system. This table shows some of these parameters for the 9 planets revolving around the Sun. The table contains the semi-major axis of the planetary orbit, the orbital period, the orbital eccentricity, and the inclination to the ecliptic for each planet. If we compare the values of the semi-major axes measured in 10 to 8 kilometers, we can see that the average distances of the outer planets are 40 to 60 times greater than those for the inner planets. We can also see big differences in the orbital periods, which are only few months in the case of Mercury and Venus, and hundreds of years for Neptune and Pluto. In order to check the validity of Kepler's third law for these data, let us compute the proportionality constant appearing in the law, that is the ratio of the cube of the major semi-axis of the orbit to the square of the period for any planet. For Mercury, this fraction is equal to the cube of 0.591 times 10 to 8 kilometers, divided the square of 0.241 year. Since the cube of 10 to 8 kilometers divided by the square of 1 year can be written as about 1.004 times 10 to 18 cubic meter per second squared, we obtain about 3.335 times 10 to 18 cubic meter per second squared. If we compute the same fraction for all the other planets in the solar system, then the result will be the same, indicating it is a constant for any celestial object revolving around the Sun, as stated in the third law. By considering the data series for orbital eccentricity, we can conclude that Mercury and Pluto have the most eccentric elliptical orbits. However, the orbits all the planets in the solar system have small eccentricities, and the planets revolve around the Sun in almost circular orbits. In the last column of the table, we can see the inclination angles of the orbits to the ecliptic, that is to the orbital plane of the Earth. These data show that the majority of planets have elliptic orbits with moderate inclinations to the ecliptic within few degrees. Only the orbits of Mercury and Pluto have the inclination angles of 7 and 17 degrees respectively. As an illustration, we show the relative size and inclinations of the orbits of the gas giants and Pluto in this figure. The trajectories of the rocky planets in the inner belt of the solar system are omitted from the figure, since the average diameters of their orbits are negligible to those of Neptune and Pluto. We also see that Pluto revolves around the Sun in a highly inclined orbit, whereas the inclination angles of the orbital planes are relatively small for other planets. When we studied circular motion in dynamics, we introduced the concepts of central motion and central force. We talk about the central motion of a point mass when its acceleration has an arbitrary magnitude but always points towards or away from a fixed point. Any force producing central motion is called central force. Due to the second law of motion, we can also state that a central force acting on a body always points towards or away from a fixed point. It follows from Kepler's laws that planetary motion is a central motion, and the force acting on any celestial object orbiting the Sun always points towards the Sun. In order to prove this statement, we formulate a general theorem. This theorem states that if a point mass performs central motion, then its trajectory is a plane curve or a line in a special case, and its areal velocity is constant. Conversely, if the trajectory of a moving point mass is a plane curve and its areal velocity is constant, then the point mass performs central motion. Since Kepler's first law tells us that planets orbit in ellipses which are plane curves, and the second law states that the areal velocity of any planets is constant, then it follows from the converse of the theorem that the planetary motion is central motion. Now we prove this theorem and its converse by applying geometric methods. Let us suppose that the point mass at the instantaneous position A0 performs central motion with respect to a fixed point O. The point mass leaving the point A0 covers some distance during a small time interval delta t, and arrives at the point A1. Then the moving point mass leaves the point A1 and arrives at the point A2 after covering some distance during the time interval delta t, and so on. Since the time interval delta t is small, we can approximate the path of the motion with a series of the displacement vectors A0, A1, A1, A2, A2, A3 and so on. Each displacement vector can also be approximated by the product of the velocity of the point mass measured at the tail of the position vector and in the time interval delta t. As a result, the length of each displacement vector is proportional to the magnitude of the velocity measured at the tail of the position vector. We can construct the motion of the point-like body as follows. The body arriving at the point A1 from the point A0 would reach the point B1 after the time interval delta t, if it had no acceleration pointing towards the center O. Therefore the magnitudes of the displacement vectors A0, A1 and A1, B1 are the same. However, the change in the velocity directed towards the point O is proportional to the length of the vector A1, C1, and its vector sum with the displacement vector A1, B1 gives the true displacement A1, A2. Similarly, the body leaving the point A2 would reach the point B2 after the time interval delta t if it had no acceleration pointing toward the center O. Then the vector sum of the change of velocity proportional to the vector A2, C2 and the displacement A2, B2 gives the true displacement A2, A3, and so on. It follows from this construction that the point mass cannot leave the plane defined by the points O, A0 and A1. Since the displacement vectors A0, A1 and A1, B1 lie on the same line, the vector A1, B1 is in the plane of the triangle OA0, A1. Similarly, the vector A1, C1 lying on the line OA1 is also in this plane. Then the displacement vector A1, A2, which is the sum of the vectors A1, B1 and A1, C1, lies in the plane defined by the points O, A0 and A1. This can also be proved for the displacement vector A2, A3, and so on. As a result, the series of the displacement vectors A0, A1, A1, A2, A2, A3 and so on remains in one plane, that is the path of a point-like body performing a central motion is a plane curve. If we compare the triangles OA1, A2 and OA2, B2, we can see that they have the same area since their bases A1, A2 and A2, B2 have the same length and their heights drawn from the point O are the same. However, the triangles OA2B2 and OA2A3 have also the same area since the vector B2A3 is parallel with the line OA2 due to the parallelogram law, and the heights of the two triangles drawn from the points B2 and A3 from the common base OA2 are equal. Therefore the triangles OA1A2 and OA2A3 have the same area, indicating that the area swept out by a point mass during the time interval delta t are the same in a central motion. This proves the theorem. In order to prove the converse of the theorem, we need to demonstrate that the acceleration of the point mass at the point A2 points towards the point O, supposing that the areas of the triangles OA1A2 and OA2A3 are equal. If we construct the triangle OA2B2 such that its side A2B2 is equal to the length of the vector A1A2, then the areas of the triangles OA1A2 and OA2B2 are equal. It follows from the supposition that the triangles OA2B2 and OA2A3 have also the same area. As a result, the heights drawn form the points B2 and A3 to the common base OA2 of the triangles OA2B2 and OA2A3 must be equal to each other, that is, the displacement B2A3 must be parallel with the line OA2. Since the displacement vector B2A3 is proportional to the acceleration at the point A2, the acceleration must also parallel with the line OA2, and must point toward the center O. This proves the converse of the theorem. In the discussion about elliptic motion, we also demonstrated that the motion is central motion if the areal velocity of the point-like body traveling along an ellipse is constant. We used a polar coordinate system attached to any of the focal points from which the position vector r sweeps out equal areas in equal times. The radial coordinate is given by the magnitude of the position vector, and the azimuthal angle phi is measured between the position vector and the x-axis. Then the instantaneous acceleration of the moving point mass could be decomposed in radial and azimuthal directions. The magnitude of the radial component is given by the radial coordinate r double dot minus r times the azimuthal angle phi dot, where the dot denotes the derivative with respect to the time t. Similarly, the magnitude of the azimuthal component can be written as r times phi double dot, plus 2 times r dot times phi dot. If we write the magnitude of the areal velocity of a planet performing elliptic motion in polar coordinates, then we have 1 over 2 times r squared times phi dot. Now we assume that the areal velocity of the planet is constant. By multiplying this equation by 2 and taking its derivative with respect to the time t, we obtain the equation stating that 2 times r dot times phi dot, plus r squared times phi double dot is equal to 0. However, we can identify the left-hand side of the equation as the magnitude of the azimuthal component of the acceleration, which is 0 now. As a result, the planet has an acceleration only in the radial direction, that is towards or away from the focal point of its orbit. Therefore, the planet moving along the ellipse with constant areal velocity performs a central motion, where the sun at the focal point is the center of the motion. Kepler already supposed that his laws of planetary motion suggest the existence of forces exerted on the planets orbiting the sun. However, it was Newton who discovered the universal law of gravitation. It follows from Kepler's second law on the constancy of the areal velocity of the planets performing elliptic motion that the acceleration of any planet points toward a fixed central point due to the presence of the sun. Therefore, a central force is exerted on all the planets, that is, the force acting on them always points towards the sun. In order to determine the magnitude of such a force, let us consider the planets Venus and Neptune in the solar system, which have orbits with extremely small eccentricities. Then we can approximate their elliptic orbits with circles, and assume that these planets perform circular motion around the sun. Due to the constancy of the areal velocity of the planets, the magnitude of the velocity or the speed of the planet is approximately constant, and we can even talk about uniform circular motion. As a result, the magnitude of the centripetal force F acting on any of these planets can be written as the mass m of the planet, times the square of its constant angular velocity omega, times the radius r of its circular orbit. Here we can express the angular velocity in terms of the orbital period t, and we obtain 4 pi squared times the ratio of the mass m times the radius r to the square of the period t. Let us denote the orbital radius and the mass of Venus by r and m respectively, and the orbital radius and the mass of Neptune by r star and m star respectively. Kepler's third law states that the square of the orbital period t of Venus divided by the square of the orbital period t star of Neptune is equal to the cube of the orbital radius r of Venus divided by the cube of the orbital radius r star of Neptune. Therefore, we can write that the ratio of r cubed to t squared is equal to the ratio of r star cubed to t star squared, which is equal to a constant c. The constant c is universal for each pair of planets in the solar system, and this quantity is specific to the Sun. Then we can express the ratio of r to t squared as the constant c divided by r squared. If we substitute this expression into the magnitude of the centripetal force acting on an orbiting planet, then it can be written as 4 pi square times the constant c, times the mass m of the planet divided by the square of the orbital radius r. This formula shows that the attractive force exerted on the planet by the Sun is directly proportional to the mass of the planet, and inversely proportional to the square of the distance between the planet and the Sun. The law of action and reaction states that the planet also exerts a force on the Sun, which has the same magnitude and points in the opposite direction. Since the interaction between the planet and the Sun is symmetric, the force exerted on the Sun by the planet must be directly proportional to the mass of the Sun. Therefore, the constant c must include the mass of the Sun, and we can write the multiplicative factor 4 pi squared c as g times the mass of the Sun denoted by capital M. Here g is a universal constant, which depends on neither the mass of the planet nor the mass of the Sun. As a result, the magnitude of the attractive force acting between the Sun and the planet is equal to g times the mass capital M of the Sun times the mass m of the planet, divided the square of the distance r between the two celestial objects. Based on astronomical observations, Newton concluded that the same law of force must hold for the forces acting between the Sun and the planets, and between the planets and their moons. Furthermore, he assumed that the force exerted on the Moon by the Earth is the same kind of force as the gravitational force, or the weight attributed to the acceleration g of free-falling objects in the vicinity of the Earth. This assumption probably served as a stepping stone for Newton's theory, and it could be tested in a simple way. If the force exerted by the Earth is inversely proportional to the square of the distance from the center of the Earth, the Moon orbiting the Earth at the distance of about 60 times the radius of the Earth must have the acceleration of 60 squared, that is 3,600 times smaller magnitude while it moves towards the Earth, than the magnitude of the acceleration of the falling bodies near the Earth's surface. That is, the acceleration of the Moon towards the Earth is given by the ratio of 9.81 meter per second squared to 3,600, which is equal to about 2.73 times 10 to minus 3 meter per second squared. This value can be checked if we calculate the centripetal acceleration of the Moon by approximating its orbit with a circle. We can suppose that the Moon performs a uniform circular motion around the Earth with a radius of 60.3 times the radius of the Earth given by 6.371 times 10 to 6 meters, which is equal to 3.84 times 10 to 8 meters, whereas the orbital period of the Moon is given by 27.3 days or 2.36 times 10 to 6 seconds. For a body performing uniform circular motion, the speed v can be written as the radius r of the circle times its angular velocity omega. Since omega is given by 2 pi over the orbital period t, we obtain 2 pi times 3.84 times 10 to 8 meters over 2.36 times 10 to 6 seconds. Then the speed of the Moon is equal to 1.02 times 10 to 3 meter per second. The acceleration a in uniform circular motion is given by the ratio of the square of the speed v to the radius r, that is the square of 1.02 times 10 to 3 meter per second divided by 3.84 times 10 to 8 meters for the orbital motion of the Moon. As a result, we have 2.72 times 10 to minus 3 meter per second squared, which is almost the same value as the one obtained by applying the law of force acting between planets. This result confirms that the gravitational force of the Earth is exerted on the orbiting Moon. Similarly, the gravitational force of the Sun produces the orbital motion of the planets. Due to the third law of motion, that is the law of action and reaction, the Moon also exerts the same force on the Earth but opposite in direction. Furthermore, any planet in the solar system exerts the same force on the Sun but opposite in direction. The generalization of the law of force introduced to describe the forces acting between celestial objects was demonstrated by several experiments. Newton published the universal law of gravitation in 1686, stating that 2 point-like bodies with the masses m1 and m2 attract each other with a force which has a magnitude directly proportional to the product of the masses of the bodies, and inversely proportional to the square of the distance r between them. If the vector r points from the second body to the first one, then the force F exerted on the first body by the second one points in the direction of the unit vector r over its length. Similarly, the force exerted on the second body by the first one has the same magnitude but points in the opposite direction. The proportionality factor g is called gravitational constant, and its unit is derived from the equation describing the law of force, which gives cubic meter per kilogram times second squared. In the derivation of the universal law of gravitation, We applied Kepler's third law stating that the ratio of the cube of the orbital radius r to the square of the orbital period t is equal to a constant c for the planetary orbits in the solar system. When we calculated the constant c, we obtained about 3.36 times 10 to 18 cubic meter per second squared, which is a universal constant for each planet and specific to the Sun. By motivated this fact, we introduced the gravitational constant g in the definition, stating that 4 pi squared times the constant c is equal to the gravitational constant g times the mass m of the Sun. As a result, we can express the gravitational constant g as 4 pi squared times the constant c divided by the solar mass m. Since the mass of the Sun is equal to 1.988 times 10 to 30 kilograms, the gravitational constant g is equal to 6.67 times 10 to minus 11 cubic meter per kilogram second squared. This value is obtained by approximating the elliptic orbits of the planets with a circle, but the gravitational constant could also be measured with high precision. Before presenting the experiment measuring the accurate value of the gravitational constant, we note that the gravitational force acting between bodies which are not point-like but very far from each other can be determined with calculations applying the universal law of gravitation. Cavendish experiment was the first experiment allowing the determination of the accurate value of the gravitational constant, although its original aim was to measure the density of the Earth. The method applied in the experiment was developed by John Michel, a geologist and astronomer who also designed an apparatus for the measurement. Since Michel died in 1793, Henry Cavendish, an English chemist and physicist, rebuilt the apparatus based on Michel's plan and performed the experiment. Cavendish carried out several measurements between 1797 and 98, where the force of gravitational attraction was measured between two pairs of lead spheres to determine the relative density of Earth with respect to the spheres. The apparatus depicted in the figure from Cavendish's paper was a torsion balance, which was a horizontal wooden rod suspended freely from a wire, and two lead spheres hung from each end of the rod serving as an arm of the balance. Two large lead spheres were also placed at each end of the arm on its alternate sides such that they were near the smaller spheres. Although in Michel's design the small lead balls were hung in a narrow case to defend them from the wind, Cavendish placed the apparatus in a closed space for a full protection, and observed the position of the arm with a telescope through a hole in the wall of the room. The size of the torsion balance also shown in this schematic figure was relatively big. The length of the horizontal rod was about 1.8 meters, whereas the diameters of the small and big spheres were about 5 and 30 centimeters, respectively. Therefore, the characteristic length given by the sizes and the relative positions of the spheres were much smaller than the distance between the pairs of spheres at the opposite ends of the rod. Due to the difference in their sizes, the weights of the small spheres were only 0.73 kilograms, whereas the bigger ones had the weights of 158 kilograms. Since the small spheres and the big ones were close enough to each other, the gravitational attraction between them was able to rotate the arm, twisting the wire used for the suspension. However, the rotation was counteracted by the restoring force from the twist in the wire, and the arm stopped its rotation when it reached an angle where the twisting force and the gravitational force acting between the spheres became balanced. Actually, the arm was not at rest but oscillated about the position of the balance, performing a motion from side to side like a horizontal pendulum. Cavendish measured the position of the arm by using scales attached to the arm and the case enclosing the small spheres. He observed the three successive maxima of the displacement of the oscillating arm and averaged the second and the third maxima. A modern solution to the measurement of the position of the arm can be achieved if we apply a light source emitting light on a mirror mounted on the arm, and read the position of the reflected light beam in a scale. If the arm in the mirror rotates, then the reflected light beam will hit the scale somewhere else, and the position of the arm can be determined from the angle alpha measured between the initial and final directions of the beam. We can measure the distance covered by one of the moving small spheres during a short time right after the big spheres were placed near the small ones and the arm starts to oscillate. In the beginning of the motion, the restoring force exerted on the sphere by the twisted wire is still negligible, and the gravitational attraction can be considered constant between the spheres due to the very slowly decrease in the distance between them. Therefore, the initial motion of the sphere can be approximated as a uniformly accelerating linear motion, where the distance s is equal to 1/2 times the acceleration a of the sphere, times the square of the elapsed time t. Since the acceleration a is equal to the force F acting on the sphere divided by its mass m, we can substitute the law of universal gravitation into this equation, stating that the force F is equal to the gravitational constant g, times the mass M of the big sphere times the mass m of the small sphere, divided by the square of the distance r between the two spheres. Then we can express the gravitational constant g as 2 times s times r squared over m times t squared. Here the mass m of the big sphere is given, and the distance s depending on the angle alpha of the deflection of the light beam, the elapsed time t, and the distance r between the spheres are measured. As a result, we can determine the value of the universal gravitational constant in a measurement performed with the torsion balance. More precise measurements with torsion balances placed in vacuum or other methods using sophisticated atom interferometers provided an accurate value of the gravitational constant g, which is 6.6743 times 10 to minus 11 cubic meter per kilogram second squared. If we know the value of the gravitational constant, then we can apply the universal law of gravitation to determine the mass of celestial objects in our solar system. In the case of the Earth, we proceed as follows. The weight of a body with a mass m given by m times the gravitational acceleration g on the Earth's surface at the distance of 6,370 km from its center is equal to the gravitational force exerted on the body by the Earth. Therefore, the mass m times the magnitude of the gravitational acceleration g is equal to the gravitational constant capital G times the ratio of the Earth's mass m e times the mass m of the body to the square of the Earth's radius re. We can express the mass me of the Earth as the ratio of the gravitational acceleration g to the gravitational constant capital G times the square of the Earth's radius re. That is, 9.81 meter per second squared divided by 6.67 times 10 to minus 11 cubic meter per kilogram second squared, times the square of 6.37 times 10 to 6 meters. Then the mass of the Earth is equal 5.9 times 10 to 29 kilograms, or about 6 times 10 to 21 tons. We can also calculate the average density of our planet, if we divide the mass of the Earth by its volume, that is by 4 pi over 3 times the cube of its radius re. By substituting the numerical values into this equation, we obtain 5,515 kg per cubic meter or about 5.5 gram per cubic centimeter. Since the average density of the rocks on Earth's surface is equal to 2.5 gram per cubic centimeter, the core of the Earth must be much more dense than the average value of 5.5 gram per cubic centimeter. We already saw that the elliptic orbit of Venus can be approximated as a circle with the radius of 1.0821 times 10 to 8 kilometers due to its small eccentricity. In this approximation, Venus performs a uniform circular motion around the Sun with a period of 0.615 year. Then we can state that the centripetal force acting on Venus is equal to the gravitational force exerted on the planet by the Sun. On one hand, the magnitude of the centripetal force acting on Venus is given by its mass m times the magnitude of its centripetal acceleration, that is the mass m times 4 pi squared times the orbital radius r of Venus, divided by the square of its orbital period t. On the other hand, the magnitude of the gravitational force exerted on Venus by the Sun can be written as the gravitational constant g, times the mass capital M of the Sun times the mass m of Venus, divided by the square of its orbital radius r. As a result, we can express the mass capital M of the Sun from this equation as 4 pi squared over the gravitational constant g, times the cube of the average orbital radius r of Venus divided by the square of its orbital period t. By substituting the numerical values into this equation, we obtain 1.99 times 10 to 30 kilograms, which is about 332,000 times greater than the mass of the Earth. This method can be applied to compute the masses of those planets that have moons by measuring the orbital radii and periods of their moons. Finally, we note that Newton's law of gravitation is far more universal than Kepler's law applied to its derivation, and represents a deeper understanding on nature and physics. By applying the universal law of gravitation in Newton's second law of motion, we can derive the equation of motion of a planet orbiting the Sun. Then the equation of motion of the planet states that the mass m of the planet times the second-order derivative of the position vector r of the planet pointing from the Sun to the planet, is equal to minus the gravitational constant g, times the mass capital M of the Sun times the mass m, divided by the square of the length of the position vector r, times the position vector r divided by its length. Here the instantaneous velocity v of the planet is simply the derivative of the position vector r with respect to the time, whereas the acceleration of the planet is given by the second-order time derivative of its position vector r. Kepler's three laws can be derived from this equation of motion in a mathematical way. Furthermore, the solution to the equation of motion also demonstrates that the orbit of a celestial body can be not only ellipse but also other types of conic section seen in the figure depending on the initial value condition. For example, the orbit of a comet can be parabola or hyperbola as well. The so-called perturbations, or small deviations in the orbital motion of planets from Kepler's laws could also be interpreted based on the mutual gravitational interaction between planets. In 1846, Urbain Le Leverrier, a French astronomer and mathematician, was able to calculate the mass and the orbit of an unknown planet from the perturbations of Uranus' orbit, which led to the discovery of Neptune. Generally, Newton's universal law of gravitation is the fundamental part of celestial mechanics, provides a definitive evidence for the validity of the laws of motion also discovered by Newton, and includes the law of gravitation on the surface of the Earth as a special case, stating that the weight of a body is given by its mass times the gravitational acceleration due to the Earth. There is an alternative form of Newton's second law of motion allowing us to reinterpret problems in dynamics as problems in statics. It is known as D'Alembert's principle, named after a French physicist and mathematician Jan de Rond D'Alembert. This principle can be formulated as follows. Let us start with Newton's second law of motion, where the fundamental equation of dynamics states that the mass m of a point mass times its acceleration a is equal to the vector sum f of the forces from F1 to Fn acting on the point mass. In fact, the form of the fundamental equation includes the fourth law of motion, stating that force is a vector, that is, the net force F of a system of forces acting on a body is given by their vector sum. The acceleration of a body is always measured with respect to a frame of reference, represented the reference point O here, where the position vector or pointing from the point O to the point-like body describes the instantaneous position of the body. When we studied the laws of motion, we also considered situations where the acceleration of the point mass vanishes. The interpretation of such cases was that the point mass is at rest or in equilibrium if and only if the net force of all the forces acting on the point mass is zero, that is, the forces acting on the point mass are balanced. If both the constrained and unconstrained forces acting on the point mass cancel each other out, then the point mass remains at rest, provided its initial velocity with respect to the frame of reference is zero. In other words, the vector sum of the forces from F1 to Fn vanishes, that is, the condition for the equilibrium of the mass point is the balance of the forces acting on it. Besides this condition of balance, there is another interpretation of the fundamental equation of dynamics which was introduced by D'Alembert. We can write the fundamental equation in the form stating that the net force F acting on the mass point, plus the negative product of its mass m and its acceleration a vanishes, or F1 plus F2, plus ellipsis plus Fn plus the term minus m times a is equal to 0. The negative product of the mass of the point-like body and its acceleration with respect to an inertial frame can also be considered as force, or the force of inertia as D'Alembert called it. Then the force of inertia or the inertial force F star is given by minus m times a, or minus m times the second-order derivative of the position vector r of the point mass with respect to the time. This is a fictitious force, also called pseudo-force, since it is created by motion. We have to remember that the concept of force is introduced for the effects changing the state of motion of bodies, that is, forces are the cause of motion and not the product of it. Then the fundamental equation written in the form stating the net force F acting on the point mass plus the inertial force F star produced by its acceleration vanishes, or F1 plus F2 plus ellipsis plus Fn plus F star is equal to 0. In this case, the net force F of the impressed forces and the inertial force F star defined by minus the mass m times the second-order time derivative of the position vector or of the point mass are balanced, and the point mass is in equilibrium. This form of the fundamental equation has the following interpretation. Any problem in dynamics can be formally treated as a problem in statics, if we add the inertial force to the net force of the constrained and unconstrained forces acting on the point mass. In other words, dynamics is reduced to statics since we solve actual problems in dynamics by applying methods used in statics. Although there is nothing new in such a reinterpretation of the second law of motion, it had often proven useful. Because unknown forces acting on bodies are more easily determined in equilibrium, the force analysis in problems involving several bodies can usually be simplified by using inertial forces. The original interpretation of the fundamental equation involves the dynamic interpretation of the force causing the motion. From that viewpoint, it makes no sense to talk about inertial force, since only the net force F acting on the point mass m produces its acceleration a given by the force F divided by m, and there is no other force involved in this process. As mentioned before, force is the cause of acceleration and motion by definition. Now we can also talk about the static interpretation of force. The fundamental equation only states that the net force F acting on a point mass m is equal to the mass m times its acceleration a, but does not tell anything about the concrete causal relation between force and acceleration. Therefore, we can also apply the interpretation based on D'Alembert principle, which is the static interpretation of force, stating that forces acting on a point mass are always balanced. Since the forces include inertial force here, we cannot consider force as the cause of acceleration or motion. These two interpretations of force are based on the same law of motion described by the fundamental equation. Both of them can be applied, but not simultaneously. We have already stated that D'Alembert principle can be useful from a practical point of view, since it helps us to simplify the force analysis in some problems. However, from theoretical point of view we can still ask why a moving point mass should be treated as if it were in equilibrium. Two answers can be given to this question. Firstly, motion is always relative, and the instantaneous position of a body is always determined with respect to a frame of reference. Then we can choose a frame of reference moving with the body, and observe the body in that system. The body remains at rest in the co-moving system, although the frame moving with a body accelerated by forces will not be an inertial frame. Secondly, D'Alembert's principle focuses our attention on forces and not on the moving body, and the balance of a system of forces acting on a body can be treated without referring to the state of motion of the body on which they act. Let us consider some examples for the two different interpretations of force. In the first example we study the motion of a body accelerated in the vertical direction, where we exert a force F' on the body with the mass m, and the force is greater than the weight of the body given by the mass m times the gravitational acceleration g. Then the dynamic interpretation of force tells us that the net force acting on the body is equal to the vector sum of the force F' and the weight of the body given by the mass m times the gravitational acceleration g. As a result, the fundamental equation states that the acceleration a of the body is equal to the sum of F' and m times g, divided by m. Here the magnitude of the acceleration a pointing upward is given by the magnitude of F' minus m times the magnitude of g, divided by m. The static interpretation of force tells us that the force F', the weight m times g of the body, and the inertial force minus m times a are balanced, that is their vector sum vanishes. This equation also leads to the equation shown in the dynamic interpretation of force. The second example is uniform circular motion, where a body with a mass m is attached to a string and whirled in a circle with the radius r by hand at a constant angular velocity omega. Following the dynamic interpretation of force, we can say that a force F' is exerted on the body by our hand through the string. This force produces the centripetal acceleration a given by minus the square of the angular velocity omega times the position vector r pointing from the center of the circle to the body. Then the fundamental equation of dynamics states that minus the mass m of the body times the square of the angular velocity omega times the position vector r is equal to F'. However, the static interpretation of force states that force F' and the inertial force minus m times a, or m times omega squared times r are balanced, that is their vector sum vanishes. Since the acceleration a is given by minus omega squared times the position vector r, this is the same equation as the one derived in the dynamic interpretation. The inertial force m times omega squared times r acting on the body has only meaning in the static interpretation. This force points from the center of the circle, and is called centrifugal force. In the end of this presentation on the fundamental equation of dynamics, let us summarize its main conclusions. We started with a brief overview of the fundamental assumptions and laws in dynamics, and introduced the fundamental equation of dynamics stating that the product of the mass and the acceleration of a point-like body is equal to the net force acting on the body. We also presented how to deduce some laws of force and how to determine the motion of bodies from these laws. Then we applied the fundamental equation in several examples and we studied dynamics in a variety of problems. Our first example was projectile motion, where we studied the dynamics of a point-like body accelerated by the gravitational force. We derived the equations of motion of the projectile from the fundamental law of motion and determined its kinematic variables by solving the equations. We saw that the projectile motion with parabolic trajectory is the most general motion of a point mass under the influence of gravity, provided we neglect air resistance. Another law of force studied here was Hooke's law describing the behavior of elastic forces. The law states that displacement is directly proportional to the applied or restoring force in the case of the elastic deformation of a material on which a force is applied. By applying Hooke's law in the fundamental equation of motion, we obtained the equation of motion for elastic deformation, and its solution showed that the displacement can be described by simple harmonic motion of the deformed parts of a material. We also saw that the frequency of such a periodic motion is determined by the properties of the material. Then we studied constrained motion, where objects move along given curves or over given surfaces imposed as constraints on the motion. We separated unconstrained and constrained forces in the fundamental equation of dynamics when we applied it in several examples, such as motion on inclined and horizontal planes or in the case of vertical acceleration. It also helped us to understand the operation of Atwood machine. The next topic was frictional motion, where we studied the forces exerted on bodies during the relative displacement along some contact surfaces. We presented Coulomb's law of friction, stating that these forces acting in the direction opposite to the displacement are always proportional to the applied force normal to the contact surfaces. The proportionality constant is called the coefficient of friction. We applied this law for both sliding and sticking friction, which we studied on bodies moving over horizontal and inclined surfaces. We also studied the dynamics of bodies performing uniform circular motion and determined the centripetal force acting on the body. We also presented some examples where the objects traveled along circles due to constrained and unconstrained forces exerted on them. By applying the same method, we also discussed the dynamics of bodies moving along general curves, where we determined both the tangential and centripetal forces acting on a body at an instantaneous position on the curve. Then we discussed the dynamics of a mathematical pendulum, where we derived its equation of motion by analyzing the constrained and unconstrained forces acting on the bob. We saw that the equation of motion can be reduced to the oscillator equation for small swings of the pendulum, describing a simple harmonic motion around its equilibrium position. We determined the period of motion in the general case, and compared its deviation from the period obtained for small swings as a function of its maximum angular displacement. We continued the series of applications with the dynamics of planetary motion, where we presented both the geocentric and the heliocentric models of celestial mechanics in the solar system. We introduced Kepler's three laws, providing a set of relations between the kinematic quantities of planetary orbits. The first law states that planets move in elliptical orbits with the Sun at one of two foci. The second one states that the radius vector pointing from the Sun to any planet sweeps out equal areas during equal intervals of time. The third one states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of the semi-major axes of their orbits. Based on some considerations related to the findings in celestial mechanics, we could introduce Newton's law of gravitation, describing the universal effect of gravitational mass. The universal law states that two-point masses attract each other with a force, which has a magnitude directly proportional to the product of the masses and inversely proportional to the square of the distance between them. We also presented Cavendish experiment, which demonstrated the law by measuring the gravitational force between two pairs of lead spheres. We finished this presentation with D'Alembert's principle, providing an interpretation of the laws of motion, where the fundamental equation of dynamics is formulated as a condition for force balance. As a result, problems in dynamics can be treated as the ones in statics. However, such a description is based on the concept of inertial force, where force cannot be considered as the cause of motion. In the analysis of the examples presented here, such as motion with acceleration in vertical direction or uniform circular motion, we applied this principle to illustrate the difference between the static and dynamic methods.